Section 25 of the Science, History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology, Chapter 13, Historical Geology, Part 2. In the Grand Canyon and Montana, determinable fossils have been found in the less changed sediments, but they are too few and scanty to indicate much of the life of the times. Evidences of life are not wanting in the metamorphic rocks of the eastern and northern regions, but they are indirect. The strata of crystallized limestone are indications of the presence of animal life in the Algonkian seas. The great quantities of graphite diffused through many of the schists and the beds of iron ore likewise tend to show the existence of plants at the same time. More conclusive are the determinable fossils obtained in the Belt series of Montana and in the Grand Canyon series, which include the tracks of worms, brachiopods, and fragments of large crustacea referable to the Eurypterida. Such remains imply a long antecedent history of life, the records of which remain to be discovered. With regard to the comparative value of the Precambrian rocks in the chronology of geological history, no precise statement can be made, but various circumstances show that they must represent an enormous period of time. From the general character of the Cambrian fauna, it must be regarded as certain that life had existed on the earth for a long series of ages before that fauna appeared, in order that such well-advanced grades of organization should then have been reached. One of the most interesting chapters of geological history would be supplied if some adequate account could be given of the stages of this long Precambrian evolution. The Paleozoic is the oldest of the three main groups into which the normal fossiliferous strata are divided, continues Scott. It forms the first legible volume of the Earth's history, and in interpreting it, speculation and hypothesis play a much less prominent part than in the Precambrian volume. The Paleozoic rocks are conglomerates, sandstones, shales, and limestones, with quite extensive areas of metamorphic rocks and associated igneous masses, both volcanic and plutonic. The thickness of these rocks is very great, estimated in Europe at a maximum of 100,000 feet. This does not imply that such a thickness is found in any one place, but that if the maximum thicknesses of each of the subordinate divisions be added together, they will amount to that sum. In this country, more than 25,000 feet of Paleozoic strata are exposed in the much folded and profoundly denuded Appalachian Mountains, but in the Mississippi Valley they attain only a fraction of that thickness. These rocks are, in the vast majority of cases, of marine origin, but some freshwater beds are known, and very extensive swamp and river deposits have preserved a record of much of the land life of the era, especially of its later portions. That there must have been land surfaces is abundantly shown by the immense thickness and extent of the strata, all of which were derived from the waste of the land. Both in Europe and in North America, the land areas were prevailingly toward the north and are doubtless indicated, in part, by the great regions of the Precambrian metamorphic rocks. The general character of the Paleozoic beds shows that they were, in large measure, laid down in shallow water in the neighborhood of land. Their great thickness indicates further the enormous denudation which the land areas underwent. The calculation has not been made for this country, but for Great Britain, Geikie states that the lower half of the Paleozoic group represents the waste of a plateau larger than Spain and 5,000 feet high, cut down to base level. Very widespread disturbances of the Earth's crust before the beginning of the Paleozoic era and at its close have produced well nigh universal unconformities with both the underlying Precambrian and the overlying Mesozoic rocks. At only a few points are the transitional series found. Early in Paleozoic time were established the main geographical outlines which dominated the growth of the North American continent, a growth which was for the most part steady and tranquil. These conditions may be briefly stated as the formation of a great interior continental sea, divided from the Atlantic and the Pacific by more or less extensive and variable land areas. There are thus three principal regions of continental development: those of the Atlantic and Pacific borders and the interior. In addition, the eastern border is subdivided by Precambrian ridges into subordinate areas of deposition. At the present time, the surface rocks over the eastern half of the continent are prevailingly Paleozoic, extending chiefly southward and southeastward from the great Precambrian mass of the north. Paleozoic time was of vast length, perhaps exceeding that of the combined Mesozoic and Cenozoic eras. The subdivisions of the Paleozoic are very clearly marked, locally often by unconformities, but on a wide scale by the changes in the character of the fossils. Paleozoic life possesses an individuality not less distinctly marked than that of the group of strata, which demarcates it very sharply from the life of succeeding periods and gives a certain unity of character to the successive assemblages of plants, floras, and of animals, faunas. The era is remarkable both for what it possesses and what it lacks. Among the plants, the vegetation is made up principally of cryptogams, seaweeds, ferns, club mosses, and horsetails. Especially characteristic are the gigantic tree-like club mosses and horsetails, which are now represented only by very small herbaceous forms. The only flowering plants known are the gymnosperms, the cyads, and their allies. No angiosperms have been discovered. Paleozoic forests must have been singularly gloomy and monotonous, lacking entirely the bright flowers and changing foliage of later periods. The Paleozoic fauna are largely made up of marine invertebrates, in the earlier periods entirely so, for example, so far as we have yet learned, though land life surely began before the oldest records of it yet discovered. Graptolites and hydroid corals, true corals, echinoderms, especially crinoids, cystidines and blastoids, long-hinged and hingeless brachiopods, mollusca, particularly of the nautiloid cephalopods, and the crustacean groups of trilobites and Eurypterida, are the most abundant and characteristic types of animal life. Insects, centipedes, and spiders are common toward the end of the era. Cambrian rocks contain no fossil vertebrates, but they make their appearance in the Ordovician. For long ages, the only vertebrates were fishes and certain low types allied to the fishes, but at the end of the Devonian and in the Carboniferous appeared the amphibia, followed in the Permian by true reptiles. Teleos, such as make up by far the largest part of the modern fish fauna, both marine and freshwater, as well as birds and mammals, are entirely absent from the Paleozoic. The overwhelming majority of Paleozoic species and even genera fail to pass over into the Mesozoic, and even in the larger groups, which continue to flourish, almost always a more or less complete change of structure occurs, so that Paleozoic corals, echinoderms and fishes, for example, are very markedly distinct from those which succeeded them. The difference is generally in the direction of greater primitiveness of structure in the older forms, Paleozoic types standing in somewhat the same relation to subsequent types as the embryo does to the adult. In the vast periods of time included in the Paleozoic era occurred some remarkable climatic vicissitudes. Times of widespread glaciation occurred in the Lower Cambrian of Norway and China, probably of Australia, and perhaps also of South Africa, in the Devonian of South Africa, and in the Permian of the latter region, India, Australia, and South America, perhaps also in Europe and North America. For most of the era, however, the climate appears to have been mild and equable on the whole, very much of the same kinds of animals and plants occurring in high as in low latitudes. In short, we can detect no evidence of climatic zones as being distinctly marked in those periods. So far as they are accessible to observation, the Cambrian rocks are chiefly such as are laid down in shallow water near shore, conglomerates, sandstones, and shales, which are ripple marked in a way that betrays their shoal water origin. During Cambrian times, the sea was slowly advancing over the land in North America, and the geography of the continent was very different at the close of the period from what it had been at the beginning. In the Lower Cambrian, the land areas are inferred to have been somewhat as follows. First, there was the great northern mass of crystalline Archean and Algonquian rocks, but this was probably much more extensive than the present exposures of Precambrian rocks would indicate. It probably covered the whole Mississippi Valley down to 30° north latitude and extended westward beyond the Rocky Mountains. Long narrow strips of land, alternating with narrow sounds, occupied part of New England and the maritime provinces of Canada, while an Appalachian land, whose western line is marked by the present Blue Ridge, extended eastward an unknown distance into the Atlantic. On the western shore of the Appalachian land was a narrow arm of the sea, which opened south and nearly separated this land area from the great mass of the continent. The site of the Sierra Nevada was occupied by a long narrow land, running from Puget Sound to Mexico, and another such area was found in eastern British Columbia. The Great Basin region was under water. Around these shores were laid down the coarser deposits of the Lower Cambrian, with great masses of shales and thick limestones in deeper water. Much interest necessarily attaches to Cambrian fossils, for excepting the few and obscure organic remains obtained from Precambrian strata, they are the oldest assemblage of organisms yet known. They form no doubt only a meager representation of the fauna of which they were once a living part. One of the first reflections which they suggest is that they present far too varied and highly organized a suite of organisms to allow us for a moment to suppose that they indicate the first fauna of our Earth's surface. Unquestionably, they must have had a long series of ancestors, though of these still earlier forms such slight traces have yet been recovered. Thus, at the very outset of his study of stratigraphical geology, the observer is confronted with a proof of the imperfection of the geological record. When he begins the examination of the Cambrian fauna, so far as it has been preserved, he at once encounters further evidence of imperfection. Whole tribes of animals, which almost certainly were represented in Cambrian seas, have entirely disappeared, while those of which remains have been preserved belong to different and widely separated divisions of invertebrate life. Of the plants of the Cambrian strata, nothing is surely known. Certain marks on the bedding planes of strata have been regarded as seaweeds, but they are too obscure for determination, and many are worm tracks. The fauna is principally made up of trilobites and brachiopods, but many other types are represented also. Trilobites have a more or less distinctly three-lobed body, at one end of which is the head shield, usually with a pair of fixed compound eyes. At the other end is the tail shield, and between the two shields is a ringed or jointed body made up of a variable number of movable segments. The trilobites display an extraordinary variety in form and size, in the proportions of the head and tail shields, in the number of free segments, and in the development of spines. Brachiopods are among the most abundant of Cambrian fossils. Most of them belong to the lower order of the class Inarticulata, in which the shells are mostly horny and the two valves are not articulated together by a hinge. The horny-shelled types, Linarsonia, Lingulepsis, and Lingulella, are of great interest, as they differ but little from certain brachiopods which still exist. The second order of brachiopods, the Articulata, which have calcareous shells connected by an elaborate hinge, were more common in the Upper Cambrian. Sir Roderick Murchison divided his great Silurian system primarily into two parts, Upper and Lower. This method of classification is generally followed even at the present day, although it is widely recognized that the most decided break in the entire Paleozoic group is the one between these divisions. In 1879, Professor Lapworth proposed to give due emphasis to this distinction by erecting the Lower Silurian into a separate system, the Ordovician. The name is taken from the Ordovici, the ancient British tribe which dwelt in Wales during Roman times. Lapworth's example is now largely followed in England and the United States, but on the continent of Europe the name Silurian is still retained for both systems. The passage from Cambrian to Ordovician was gradual, without any marked physical break. Only where the Upper Cambrian is sandy, as in New York, is a decided change in the character of sedimentation. In the latter part of the Cambrian a large inland sea had been established over what is now the Mississippi Valley, and, with frequent fluctuations in depth and modifications in form, it was to persist for long periods as one of the salient features of Paleozoic geography. This sea was separated from the Atlantic by the landmass called Appalachia, and on the western side it was demarcated from the Pacific by islands of undetermined size. At the end of the period came a time of widespread disturbance, upheaval, and mountain making, the traces of which are still plain in North America and Europe, especially along the Atlantic slope of each continent. The interior sea appears to have been entirely drained. At all events, no deposits transitional to the Silurian are known from that region. In the west and northwest, large areas remained land for long periods, but the interior sea was soon re-established in the Mississippi Valley. Some narrow strips of land were added to the margin of the Cambrian coasts, and on a line running through southern Ohio, Kentucky, and Tennessee, a low, broad arch, the formation of which appears to have begun early in the Ordovician, was forced up by lateral compression. This is called the Cincinnati anticline or axis. Ordovician life displays a notable advance over the Cambrian, becoming not only very much more varied and luxuriant, but also of a distinctly higher grade. During the long ages of the period also, very decided progress was made, and when the Ordovician came to its close all the great types of marine invertebrates and most of their important subdivisions had come into existence. In a general way, the life of the Ordovician is an expansion of that of the Cambrian, though but little direct connection between the two can yet be traced, and evidently there were great migrations of marine animals from some region which cannot yet be identified. Several groups of invertebrates attained their culmination and began to decline in the Ordovician, becoming much less important in subsequent periods. Thus the graptolites, the cystoidean order of echinoderms, the straight-shelled cephalopods, orthoceratites among mollusks, and the trilobites were never so abundant and so varied as during this period. In America, no plants above the grade of seaweeds and coralline algae have been discovered, but in Europe a few of the higher cryptogams are doubtfully reported. The flora of the Devonian, however, renders it highly probable that land plants were already well advanced in the Ordovician, and their remains may be discovered at any time. This must remain a matter of accident, for the known Ordovician rocks are almost all marine, which is not a favorable circumstance for the preservation of land plants. Such discoveries have indeed already been reported, but the evidence for them is not satisfactory. The general disturbance which closed the Ordovician period appears to have greatly increased the extent of the continent. An important feature in the Silurian geography of eastern North America was the establishment of the Cumberland Basin, or Appalachian Mediterranean, as it has been called. This large sea lay at the eastward of the interior sea, from which it would seem to have been either completely separated, or so nearly so that the species of marine animals inhabiting the two bodies of water were very different. The Cumberland Basin was east of the Catskill-Helderberg line in New York, and its western shore crossed New Jersey and curved westward beyond the center of Pennsylvania, where it ran southwest more or less parallel with the Appalachian line, toward which it curved eastward in southern West Virginia. The interior sea underwent a succession of oscillations much like those which had affected it during the Ordovician. It was apparently closed at the south, but extended northwestward to the Arctic Sea, while its east-west diameter had been greatly reduced from that of the Ordovician. Silurian life is the continuation and advance of the same organic system as flourished in the Ordovician, certain groups diminishing, others expanding, and some new groups now make their first appearance. In parts of North America, the Silurian passed so gradually and gently into the Devonian that it is difficult to draw the line between the two systems. Some disturbances, however, took place in Ireland, Wales, and the north of England, for in these localities the Devonian lies unconformably upon the Silurian. In other parts of Europe the transition is gradual. Comparing the rocks of the Ordovician, Silurian, and Devonian, as these are developed in the Appalachian and adjoining regions, a certain rhythmic or periodic recurrence of events may be discovered among them. Each system is characterized by a great and very widespread limestone formation, and in each the limestone is succeeded by shales or other clastic rocks, due to an increase of terrigenous material, and each was closed by a more or less widespread emergence of the sea bottom. Each began with a subsidence which gradually extended to a maximum at the time when the great limestone was formed. The parallelisms are not exact, but they are certainly suggestive. End of section 25. Section 26 of the Science, History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology, Chapter 13. Historical Geology, Part 3. The European Devonian appears in three different facies. One of these is the Old Red Sandstone, which is largely of continental origin and lies to the north. The second facies is of marine, shoal water deposits, and runs from Devonshire, through Belgium, the northern part of the Lower Rhenish, and the Harz Mountains to Poland. And the third, extending from northwestern France, through Germany to Bohemia, was laid down in deeper water. The period began in Europe with an advance of the sea over the land in many places, reaching its maximum extension in the latter part of the period, but beginning to retire before the opening of the Carboniferous. This subsidence removed the barrier which in Ordovician and Silurian times had separated the northern and southern seas, but was accompanied by the formation of closed basins farther to the north. Europe then was largely an open sea with many islands, and where the waters were sufficiently clear and free from terrigenous sediment, coral reefs were extensively formed. The Old Red Sandstone is of particular interest because owing to the peculiar circumstances of its formation it has preserved a record of Devonian land life, which, though fragmentary, is far more complete than anything we possess from the more ancient periods. These strata were laid down in closed basins, sometimes perhaps in freshwater lakes, which had only a restricted communication with the sea, and it may be that these accumulations were partly made by the wind, though there is no gypsum or salt in the beds to indicate the prevalence of desert conditions. The life of the Devonian is, in its larger outlines, very like that of the Silurian, but with many significant differences, which are due, on the one hand, to the dying out of several of the older groups of animals, and on the other, to the great expansion of forms which in the Silurian had played but a subordinate role. The fossils show that in Devonian times the land was already clothed with a varied, rich, and luxuriant vegetation of the same general type as that of whose scanty traces are found in Silurian strata. All the higher cryptogams are represented, and by large tree-like forms as well as by small herbaceous plants. The Carboniferous system of rocks has received its name from the seams of coal, which formed one of its distinguishing characteristics in many parts of the world. Both in Europe and America it may be seen passing down conformably into the Devonian and Old Red Sandstone. So insensible indeed is the gradation in many consecutive sections where the two systems join each other that no sharp line can there be drawn between them. This stratigraphical passage is likewise frequently associated with a corresponding commingling of organic remains, either by the ascent of undoubted Devonian species into the lower parts of the Carboniferous series, or by the appearance in the upper Devonian beds of species which attained their maximum development in Carboniferous times. Hence there can be no doubt as to the true place of the Carboniferous system in the geological record. In some places, however, the higher members of this system are found resting unconformably upon Devonian or older rocks, so that local disturbances of considerable magnitude occurred before or during the Carboniferous period. In Russia, and still more in China and western North America, Carboniferous rocks cover thousands of square miles in horizontal or only very gently undulating sheets. The Carboniferous is divisible into two sharply marked portions, the lower or Mississippian and upper or Pennsylvanian, a distinction which is applicable in all the continents in which the strata of this period have been carefully studied. During this period, the interior sea expanded widely, probably covering nearly the whole of the Great Plains, and most of the old land areas of the west and southwest, which had persisted through more or less of the Silurian and Devonian, were extensively submerged, probably including all of Mexico and the northern part of Central America. West of the Rocky Mountains, the Carboniferous is much the most widely extended of any of the Paleozoic systems, the sea reaching through British Columbia on both sides of the Gold Range into southeastern Alaska. The remarkable profusion of the vegetation of the Carboniferous period, not only in the Old World but in the New, suggested the idea that the atmosphere was then much more charged with carbonic acid than it now is. Undoubtedly there has been a continual abstraction of this gas from the atmosphere ever since land plants began to live on the Earth's surface, and it is allowable to infer that the proportion of it in the air in Paleozoic time may have been somewhat greater than now. But the difference could hardly have been serious, otherwise it seems incredible that the numerous insects, labyrinthodonts, and other air breathers could have existed. Most probably the luxuriance of the flora is rather to be ascribed to the warm moist climate which in Carboniferous times appears to have spread over the globe, even into Arctic latitudes. On the other hand, evidence has been adduced to support the view that in spite of the genial temperature indicated by the vegetation, there were glaciers even in tropical and subtropical regions. The life of this period is thoroughly Paleozoic and continues along the lines already marked out in the Devonian, but there are some notable changes and advances which look toward the Mesozoic order of things. The Carboniferous vegetation, Scott points out, is of very much the same character as that of the Devonian, but owing to the peculiar physical geography of the times, the plants were preserved as fossils in a much more complete state and in vastly larger numbers. The flora is composed entirely of the higher cryptogams and the gymnosperms, no plant with conspicuous flowers having come into existence, as far as we yet know. By far the most abundant of Carboniferous plants are the ferns, phyllocales, which flourished in multitudes of species and individuals, both as tall trees and as lowly herbaceous plants. Many of these ferns cannot yet be compared with modern ones, because the organs necessary for trustworthy classification have not been recovered, and such are named in accordance with the venation of the leaves. In other cases, the comparison with existing ferns may be definitely made, and these remains show that many of the modern families have representatives in the Carboniferous forests and swamps. In North America, the Permian followed upon the Carboniferous with hardly a break, so that the distinction between the two systems must be made entirely upon the fossils, which change very gradually, by drawing a somewhat arbitrary line of demarcation. In various countries there is no general agreement regarding the upper boundary of the Carboniferous. The lower Permian of Europe is remarkable for the great masses of volcanic rocks, Lava flows and tuffs which it contains, and which occur in Great Britain, France, Germany, and the Alps. This is in strong contrast to the corresponding American series, which gives no evidence of vulcanation. The animals and plants of the Permian are transitional between those of the Paleozoic and those of the Mesozoic eras. Here are found the last of many types which had persisted ever since Cambrian times, associated with forms which represent the incipient stages of characteristic Mesozoic types, together with others peculiar to the Permian. The flora of the lower Permian is decidedly Paleozoic in character, and that of the upper Permian is decidedly Mesozoic, so that if the line dividing these two great eras were drawn in accordance with the vegetation, it would pass through the Permian. Even in the lower Permian, however, the change from the Carboniferous flora is a marked one, a change which may be largely explained by the increasing aridity of the climate. Mesozoic formations have been grouped in three great divisions, which, though first defined in Europe, are found to have their representative series of rocks and fossils all over the world. The oldest of these is the Trias or Triassic system, followed by the Jurassic and Cretaceous. The life of the Mesozoic, Scott continues again, constitutes a very distinctly marked assemblage of types, differing both from their predecessors of the Paleozoic and their successors of the Cenozoic. In the course of the era, the plants and marine invertebrates attained substantially their modern condition, though the vertebrates remained throughout the era very different from later ones. Even in the vertebrates, however, the beginnings of the newer order of things may be traced. In the earlier two periods, the Triassic and Jurassic, vegetation is almost confined to the groups of ferns, cycads, and conifers, but with the Cretaceous come in the angiosperms, both monocotyledons and dicotyledons, and since then the changes have been merely in matters of detail. Among the Crustacea, the trilobites and eurypterids went out, but all of the modern groups were well represented, though many of the Mesozoic genera are no longer to be found in the seas of today. Insects reached nearly their modern condition so far as the large groups are concerned: butterflies, bees, wasps, ants, flies, beetles, etc., being added to the older orthopters and neuropters. Fishes became modernized before the close of the era, the bony fishes having acquired their present predominance. The amphibia took a subordinate place, and after flourishing for a time, the great Stegocephalia died out, leaving only the pygmy salamanders and frogs of the present. Birds and mammals made their first appearance, the former advancing rapidly to the nearly present grade of organization, though not reaching their present diversity, while the mammals remained throughout the era very small, primitive, and inconspicuous. The most significant and characteristic feature of Mesozoic life is the dominance of the reptiles, which in size, in numbers, and in diversified adaptation to various conditions of life, attained an extraordinary height of development. The Mesozoic is called the era of reptiles because these were the dominant forms of life. They filled all the roles now taken by birds and mammals. They covered the land with gigantic herbivorous and carnivorous forms. They swarmed in the sea, and as literal flying dragons, they dominated the air. At the present time there are only 5 orders of reptiles in existence, and of these only the crocodiles and a few snakes attain really large size. In the Mesozoic era, no less than 25 reptilian orders flourished, and many of them were gigantic members. Some were the largest land animals that ever existed, and the sea dragons rivaled the whales in size. Nothing so clearly shows that the Mesozoic era is a great historical fact as the dominance of its reptiles. The Triassic period is so named from the very conspicuous threefold subdivision of this system of strata in Germany, where its rocks were first studied in detail and where they occupy a greater area than in any other European country. The German Trias is, however, not the usual facies of the system, but a very peculiar one, and cannot be taken as the standard of comparison for most other countries. In the early part at least of the period, both North and South America extended farther east than at present, and no marine Triassic rocks are known on the Atlantic slope of either continent but they are extensively displayed on the Pacific side. The land barrier, which during the Paleozoic era had bounded the Great Basin Sea on the west, was submerged, and the Pacific extended over the site of the Sierras, covering western Nevada and sending a gulf into southeastern Idaho, and in British Columbia it transgressed eastward across the present mountains, and it covered part of the coast of Alaska. On the Atlantic side of North America the course of events is entirely different. In the latter half of the period was formed a series of long narrow troughs running closely parallel to the trend of the Appalachian Mountains, but separated from them by the ridges of metamorphic and crystalline rocks which follow those mountains to the east, and which then probably had a considerable altitude, much greater than at present. In those troughs was laid down the enormous thickness of non-marine rocks which constitute the Newark series and are now found in several disconnected areas from Nova Scotia to North Carolina. Triassic life is entirely different from anything that had preceded it, though the way for the change was already preparing in the Permian. The Upper Permian, if classified by its plants alone, would be referred to the Mesozoic rather than to the Paleozoic. Therefore it is not surprising that the Triassic flora is very similar to that of the Upper Permian, though the Upper Trias marks a decided advance among the plants. Among the animals a considerable number of surviving Paleozoic types persist into the Trias which did not pass into the Jurassic. William Smith, the father of historical geology, was the first to work out the divisions of the Jurassic, which he did early in the last century. Smith's name for the system, Oolitic, has been abandoned in favor of the term Jurassic, which was first used by Brongniart and Humboldt. It was taken from the Jura Mountains of Switzerland, where the rocks of this system are admirably displayed. In Europe the Jurassic has long been a favorite subject of study because of the marvelous wealth of beautifully preserved fossils which it contains. For this reason the Jurassic is known with a fullness of detail such as has been acquired regarding very few of the other systems, and no less than 30 well-defined subdivisions have been traced through many countries of the Old World. In this country the Jurassic is ill represented and its divisions are not clear. The life of the Jurassic has been preserved in wonderful fullness and variety, but with comparatively few exceptions our knowledge of it has been principally derived from Europe, where a host of eminent geologists have long studied the great wealth of material. The contrast between North America and Europe in regard to the relative abundance of Jurassic marine fossils is seen from the fact that while in Great Britain alone more than 4,000 species have been described, in America hardly 1/10 of that number has so far been found. The flora of the Jurassic differs little on the whole from that of the Trias, and is made up of ferns, horsetails, cycads, conifers and ginkgos. The name Cretaceous is derived from the Latin word for chalk, creta, because in England, where the name was early used, the thick masses of chalk are the most conspicuous members of the system. Though first made known in England, the main subdivisions of the Cretaceous, as employed in geological literature, bear French names which have proved themselves better adapted to general use. In very marked contrast to the scanty development of the Jura, the Cretaceous strata of North America are displayed on a vast scale and cover enormous areas of the continent, eloquent witnesses of the great geographical changes in that long period. Continental, estuarine, and marine rocks are all well represented, and in consequence our information regarding the life of North America and its seas during Cretaceous times is incomparably more complete than it is for the Triassic and Jurassic. It was during the Upper Cretaceous that the great subsidence took place which affected nearly all parts of the continent and brought the sea in over vast areas where for ages had been dry land. South of New England the Atlantic coastal plain was submerged, and in New Jersey at least the waters covered even the nearly base-level Triassic belt, bringing the sea up to the foot of the crystalline highlands. The lowlands of Maryland, Virginia and the Carolinas, and all of Florida were under the ocean, and the Gulf of Mexico was extended northward in a great bay, the Mississippi embayment, covering western Tennessee and Kentucky and extending into southern Illinois. In the southern region, the Lower Cretaceous was terminated by an upheaval which caused the Comanchian Sea to withdraw from Texas and the area to the west and north of it. This mid-Cretaceous land epoch must have continued for a considerable time, permitting extensive denudation and complete change in the fauna. Wherever the marine Upper Cretaceous is in contact with the Comanche limestones north of Mexico, the two are unconformable, and no species of animal is known to pass from one to the other. In Mexico, the Lower Cretaceous passes into the Upper without a break, the disturbances there taking place at a later date. The Mesozoic era was closed in the west, as the Paleozoic had been in the east, by a time of great mountain making, and to this movement is attributed the formation of most of the great western mountain chains. From the Arctic Ocean to Mexico, the effects of the disturbance are apparent. The Rocky Mountains, the Wasatch and Uinta Mountains, the great plateaus of Utah and Arizona, and the mountains of western Texas date from this time, though subsequent movements have greatly modified them. Vast volcanic outbreaks accompanied the upheaval, which was on a far grander scale than the Appalachian Revolution had been. The life of the Cretaceous displays so great an advance over that of the Jurassic that the change may fairly be called a revolution. In the latter part of the Lower and in all of the Upper Cretaceous of North America, the flora assumes an almost completely modern character, and nearly all of our common kinds of forest trees are represented: sassafras, poplars, willows, oaks, maples, elms, beeches, chestnuts, and very many others. A new element is the monocotyledonous group of palms, which speedily assumes great importance. Cretaceous animals are sufficiently different from those of the Jurassic, but change is not so revolutionary as has been found among the plants. The life of the Cenozoic era is very clearly demarcated from that of the Mesozoic, though many modern characteristics began in the Cretaceous or even earlier. The plants and invertebrate animals nearly all belong to genera which are still living, and the proportion of modern species steadily increases as we approximate the present time. The fishes, amphibia, and reptiles differ but little from those of modern times, and the birds take on the diversity and relative importance which characterize them now. Above all, the mammals undergo a wonderful expansion and take the place of the vanished reptiles, giving to Cenozoic time an altogether different character from all that went before it. The great geographical and climatic changes produce migrations of land animals and plants upon a grand scale, from continent to continent and from zone to zone, the result of which is the distribution of living beings over the earth's surface as we find it today. The Tertiary period witnessed the development of the present distribution of land and sea and the final upheaval of most of the great mountain chains of the globe. Some of the most colossal disturbances of the terrestrial crust, of which any record remains, took place during these periods. Not only was the floor of the Cretaceous sea upraised into low lands with lagoons, estuaries, and lakes, but afterwards, throughout the heart of the Old World, from the Pyrenees to Japan, the bed of the early Tertiary or Nummulitic Sea was upheaved into a succession of giant mountains, some portions of that seafloor now standing at a height of at least 16,500 feet above the sea. During Tertiary time there was an abundant manifestation of volcanic activity. After a long quiescence, during the succession of Mesozoic periods, volcanoes broke forth with great vigor both in the Old and the New World. Vast floods of lava were poured out and a copious variety of rocks was produced, ranging from highly basic basalts, limburgites and periodites, to rhyolites, quartz felsites, and granites. The name Tertiary was given by Cuvier and Brongniart early in the last century to the succession of marine, brackish water, and freshwater beds in the Paris basin. Sir Charles Lyell, many years later, proposed the division of the Tertiary into three parts: Eocene, from the Greek eos, the dawn, and kainos, recent; Miocene, maion, less, and kainos; and Pliocene, plion, more, and kainos, a scheme which is still used today, modified by Bayreich through the insertion of a fourth epoch, the Oligocene. Oligos little or in small degree, and Kainos. Last of all, the Lower Eocene has been separated under the name Paleocene. Paleos, ancient, as in Paleozoic, a change proposed 30 years ago by the botanist Schimper, but only lately coming into wider favor. It has become customary to distinguish between the older and newer parts of the Tertiary by grouping together the Eocene and Oligocene into the Paleogene and the Miocene and Pliocene into the Neogene. End of section 26. Section 27 of the Science, History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology, Chapter 13, Historical Geology, Part 4. The post-tertiary or quaternary portion of the geological record includes the various superficial deposits in which nearly all the mollusca are of still living species. It is usually subdivided into two series. 1. An older group of deposits in which many of the mammals are of extinct species. To this group the names Pleistocene, Post-Pliocene, and Diluvian have been given. And 2. A latter series wherein the mammals are all, or nearly all, of still living species, to which the names recent, alluvial, and human have been assigned. These subdivisions, however, are confessedly very artificial, and it is often exceedingly difficult to draw any line between them. The gradual refrigeration of climate at the close of the Tertiary ages affected the higher latitudes alike of the Old and the New World. As the cold increased, says Geikie, the whole of the north of Europe came eventually to be buried under ice, which, filling up the basins of the Baltic and North Sea, spread over the plains even as far south as close to the site of London, and in Silesia and Galatia to the 50th parallel of latitude. Beyond the limits reached by the northern ice sheet, the climate was so arctic that snowfields and glaciers stretched even over the comparatively low hills of the Lyonnais and Beaujolais in the heart of France. The Alps were loaded with vast snowfields, from which enormous glaciers descended into the plains on either side, overriding ranges of minor hills on their way. The Pyrenees were in like manner covered, while snowfields and glaciers extended southward for some distance over the Iberian Peninsula. In North America also, Canada and the eastern states of the American Union, down to about the 40th parallel of north latitude, lay under the northern ice sheet. Owing mainly to the direction of the prevalent moisture-bearing winds, the snowfall was greatest toward the west and northwest, and in the direction of Scandinavia, the ice sheets attained their greatest thickness. The Scandinavian ice joined that which spread over Britain, where the dimensions of the sheet were likewise great. Many mountains in the Scottish Highlands show marks of the ice sheet at heights of 3,000 feet and more. If to this depth be added that of the deep lakes and fjords, which were filled with ice, it is evident that the sheet may have been as much as 4,000 or 5,000 feet thick in the northern parts of Britain. This vast icy covering, like the Arctic and Antarctic ice sheets of the present day, was in continual motion, slowly draining downward to lower levels. Toward the west its edge reached the sea, as in Greenland now, and must have advanced some distance along the seafloor until it broke off into bergs that floated away northward. Toward the south and east it ended off upon land, and no doubt discharged copious streams of glacier water over the ground in its front. In northern Germany, Denmark, Finland, and Scandinavia, the southern limits at which the ice rested a long while before retiring are indicated by long winding ramparts of detritus, or end moraine. In North America also, the southern edge of the ice sheet is marked by similar terminal moraines, which are well displayed from Pennsylvania to Dakota. When this glaciation took place, the terrestrial surface of the northern hemisphere had acquired the main configuration which it presents today. The same ranges of hills and lines of valleys which now serve to carry off the rainfall served then to direct the results of the snowfall seaward. The snow sheds of the Ice Age probably corresponded essentially with the watersheds of the present day. Yet there is evidence that the coincidence between them was not always exact. In some cases, the snow and ice accumulated to so much greater a depth on one side of a ridge than on the other, that the flow actually passed across the ridge, and the detritus was carried out of one basin into another. A remarkable instance of this kind has been observed in the north of Scotland, where so thick was the ice sheet that fragments of rock from the centre of Sutherland have been carried up westward across the main water parting of the country and have been dropped on the western side. In North America also, abundant evidence is afforded of a northern ice sheet, which overrode Canada and the eastern states, southward to about the 40th parallel of latitude in the valley of the Missouri. Several centers of dispersion have been noted from which this ice moved outward, chiefly in a general southerly direction, but in the middle part the ice streamed northward into the Arctic Ocean. The great mountain ranges farther south likewise nourished the numerous valley glaciers which radiated outward from the high ground. As great oscillations of climate took place during the Ice Age, and in some cases probably lasted for a long time, the plants and animals both of land and sea could hardly fail to be seriously affected. During the cold intervals, northern forms would probably migrate southward, and in the warmer episodes, southern forms would push their way northward. The Arctic terrestrial animals include the mammoth, woolly rhinoceros, musk sheep, reindeer, Arctic fox, and lemming. The marine invertebrate fauna shared, though in a less degree, the effects of the meteorological and geographical changes. During the times of great cold, northern species found their way southward, some of them even as far as the basin of the Mediterranean. The cause of the remarkable change of climate during the late Tertiary and post-Tertiary time has given rise to much discussion, but is still without a completely satisfactory explanation. Some writers have favored the view that there has been a change in the position of the Earth's axis, or its center of gravity. Others have suggested that the Earth may have passed through hot and cold regions of space. Others again, and notably Lyell, have called in the effects of stupendous terrestrial changes in the distribution of land and sea, on the assumption that elevation of land about the poles must cool the temperature of the globe, while elevation round the equator would raise it. But the amount of geographical transformation thus involved was so great and the evidence for it appeared to be so slender that geologists generally have been reluctant to accept this explanation. In the difficulty of accounting for the phenomena by any feasible operation on the Earth itself, they by degrees accustomed themselves to the belief that the cold of the glacial period was not due to mere terrestrial changes, but was to be explained somehow as the result of cosmical causes. Among the recent attempts to deal with the problem of the Ice Age is the hypothesis proposed by Professor Chamberlain, on the basis of variations in the amount of carbon dioxide in the air. It is founded on the capacity of that gas for absorbing heat and to the effect that might be produced on the temperature of the air by even a comparatively small increase or diminution in the proportion of the gas. The suggestion is that while there is a general tendency to the diminution of that proportion, there arise from time to time conditions, such as great volcanic discharges, whereby much carbonic dioxide is supplied to the atmosphere. On this view, the glacial period would mark a time of great depletion of the gas, while the Arctic Miocene flora would indicate a time of comparative enrichment. Other geologists have turned back to the idea of geographical changes. That considerable oscillations of the relative levels of land and sea took place during the Ice Age has been clearly determined. The general result of investigation favors the opinion that the land in the early part of that period stood much higher than now over the northern regions of Europe and North America. If one accepts the conclusions drawn from the prolongation of land valleys upon the sea floor to a depth of many hundred feet, and from the distribution of dead littoral and shallow water shells down to depths of 6,000 or 8,000 feet in the North Atlantic, it can be seen that a vast area of highland would, under these conditions, have existed. This higher elevation would undoubtedly tend to lower the temperature. Some of the upraised parts of the seafloor might deflect warm ocean currents and thus still further increase the cold in the higher latitudes. But no satisfactory attempt has yet been made to trace out these changes geographically on actual evidence of their having occurred and to connect them with the phenomena of the Pleistocene period. The long succession of Pleistocene ages, shaded without abrupt change of any kind into what is termed the human or recent period, the Ice Age or Glacial period, may indeed be said still to exist in Europe. The snowfields and glaciers have disappeared from Britain, France, the Vosges, and the Harz, but they still linger among the Pyrenees, remain in large mass among the Alps, and spread over wide areas of northern Scandinavia. This dovetailing or overlapping of geological periods has been the rule from the beginning of time, the apparently abrupt transitions in the geological record being due to imperfections in the chronicle. The human period, resumes Geikie, is above all distinguished by the presence and influence of man. It is difficult to determine how far back the limit of the period should be placed. The question has been asked whether man was coeval with the Ice Age. To give an answer, we must know within what limits the term Ice Age is used and to what particular country or district the question refers, for it is evident that even today man is contemporary with the Ice Age in the Alpine valleys and in Finland. There can be no doubt that he inhabited Europe after the greatest extension of the ice. He not improbably migrated with the animals that came from warmer climates into this continent during interglacial conditions, but that he remained when the climate again became cold enough to freeze the rivers and permit an Arctic fauna to roam far south into Europe is proved by the abundance of his flint implements in the thick river gravels, into which they no doubt often fell through holes in the ice as he was fishing. The proofs of the existence of man in former geological periods are not to be expected solely or mainly in the occurrence of his own bodily remains, as in the case of other animals. His bones are indeed now and then to be found, but in the vast majority of cases his former presence is revealed by the implements he has left behind him, formed of stone, metal, or bone. The history of the Bronze and Iron Ages in Europe is told in great fullness, but belongs more fittingly to the domain of the archaeologist, who claims as his proper field of research the history of man upon the globe. The remains from which the records of these ages is compiled are objects of human manufacture, graves, cairns, sculptured stones, etc., and their relative dates have in most cases been decided, not upon geological but upon archaeological grounds. When, however, the sequence of human relics can be shown by the order in which they have been successively entombed, the inquiry is strictly geological and the reasoning is as logical and trustworthy as in the case of any other kind of fossils. The age of the earth is another matter which geologists must needs speak of in terms of extreme guardedness. Reasoning by analogy, it is true, there is a certain standard to be secured. Thus, for example, when it is discovered that water flowing at a certain speed cuts away the particles of a certain rock so many fractions of an inch in a decade, it is assumed that where so many feet have been cut away from a certain rock by the influence of water, the proportion so cut away must represent so many multiples of the fraction of an inch cut away in a decade. And therefore the time that has been since the beginning of the cutting away of that gorge, such as Niagara, is an equivalent number of multiples of the decade of years. But while this affords an excellent basis for rough estimation, it is not to be forgotten that it acts entirely on the assumption that matter was in those early days as it is now, and that the forces are unchanged. This assumption, however useful, cannot be termed strictly scientific, for there is no means of determining whether the original groove, for example, may not have been made in the time when the rock was in a viscous state, or even so superheated that water would cause violent fractures, since worn smooth. The same holds true for sedimentation. A certain land is regarded as being so many thousands or millions of years in age because of the rate at which it has been laid down in sediment. But geologists are becoming more wary of this, especially since the discovery of some coins in a bog in Germany, which, according to the estimates of the laying down of peat, must have been 18,000 years old, and yet which were found to have the stamp of Claudius Caesar. The physical argument, moreover, that changes in plants and animals have taken a long while to produce is purely dependent upon a certain theory of variation in biology, a theory by no means certain or approved. Thus, to give the best known modern instance, in the space of 10 years, Hugo de Vries, the great Amsterdam botanist, has observed a variation in the evening primrose, which is permanent and reproductive, yet which, according to the older ideas of infinitely slow variation, would have been presumed to have taken hundreds, if not thousands, of years. More, if the forces of life were stronger in their youth, as is not an impossible assumption, changes could and probably would occur with greater variation and at higher speeds than at the present time, when the force has been worked over and over for myriad centuries. An ingenious geological argument has been based by Professor J. Joly of Trinity College, Dublin, on the quantity of sodium present in the water of the ocean as a measure of the age of the earth. He assumes that the sodium contained in that water was not derived from the primeval atmosphere or the original constitution of the ocean, but has been supplied in the long course of geological time by the denudation of the land and the consequent removal of the material in solution from the terrestrial rocks. He arrives at the conclusion that if the present annual supply be taken as a measure of what has been the rate in past time, a period of between 90 and 100 millions of years has elapsed since the ocean began to receive its tribute of chemical solution from the land. The geological argument for the age of the earth may be summed up thus. The geological evidence indicates an interval of probably not much less than 100 million years since the earliest forms of life appeared upon the earth and the oldest stratified rocks began to be laid down. The physical argument as to the age of this planet is based upon three kinds of evidence. 1. The internal heat and rate of cooling of the earth. 2. The tidal retardation of the earth's rotation. And 3. The origin and age of the sun's heat. 1. Applying Fourier's theory of thermal conductivity, Lord Kelvin pointed out as far back as the year 1862 that the superficial consolidation of the globe could not have occurred less than 20 million years ago, or the underground heat would have been greater than it is, nor more than 400 million years ago, otherwise the underground temperature would have shown no sensible increase downward. He would now restrict the time to between 20 and 40 millions. 2. The reasoning from tidal retardation proceeds on the admitted fact that owing to the friction of the tidal wave, the rotation of the earth is retarded, and is therefore slower now than it must have been at one time. Lord Kelvin contends that had the globe become solid some 10,000 million years ago, or indeed any high antiquity beyond 100 million years, the centrifugal force due to the more rapid rotation must have given the planet a very much greater polar flattening than it actually possesses. 3. The third kind of evidence leads to results similar to those derived from the two previous lines of reasoning. It is based upon calculations as to the amount of heat that would be available by the falling together of masses from space, which by their impact gave rise to our sun, and the rate at which this heat has been radiated. Assuming that the sun has been cooling at a uniform rate, Professor Tate concluded that it cannot have supplied the earth, even at the present rate, for more than 15 or 20 million years. Lord Kelvin also believes that the sun's light will not last more than 5 or 6 millions of years longer. Believing that almost anything is possible as to the present internal state of the earth, Professor Perry concluded an article in Nature in these words: "To sum up, we can find no published record of any lower maximum age of life on earth, as calculated by physicists, than 400 millions of years. From the three physical arguments, Lord Kelvin's higher limits are 1,000, 400, and 500 million years, I have shown that we have reasons for believing that the age, from all these, may be considerably underestimated. It is to be observed that if we exclude everything but the arguments from mere physics, the probable age of life on the earth is much less than any of the above estimates. But if the paleontologists have good reasons for demanding much greater time, I see nothing from the physicist's point of view which denies them 4 times the greatest of these estimates. End of section 27.
Section 28 of The Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in January 2016. The Science History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology. Chapter 14. Crystallography, Part 1. The physicist, as a result of his studies into the structure of different kinds of matter, has concluded that every body is built up of minute particles called molecules, which are much too small to be perceived even by the strongest microscope. When a liquid turns into a solid, because the temperature falls, as when water freezes, or liquid sulfur or molten iron hardens when cooling, the force of cohesion comes into play to bind these molecules together into a rigid mass. So, also, when by slow evaporation from solution, as of salt or alum in water, the dissolving liquid is removed, the substance in solution also passes back into the solid form under the action of this same force of cohesion. Thus, the solid is formed from the liquid by the action of the forces acting between these little particles. Further, if the molecules are all of one kind, as in a given chemical substance, and if there are no hindering causes, these molecules will build themselves up after some regular pattern, and the external result is the geometrical form which is called a crystal. This regular building of the molecules, which may take place from a liquid, happens also, even more perfectly, when a solid is formed direct from a gas. Water vapor in the air, if cooled down sufficiently, is formed into the solid snow, and the little snow crystals that fall silently through the atmosphere are often of wonderful regularity and beauty of form. In nature it often happens that the building process cannot go on freely, and imperfect crystals, or perhaps a mass with only a confused crystalline structure and without distinct external form, is all that is produced. The quartz, feldspar, and mica in the rock called granite usually have formed together in such a way that neither one has had an opportunity to build itself up into perfect crystals, and yet the scientist who understands the optical study of thin sections of a rock in polarized light can prove that each grain, formless though it may be externally, has all the internal molecular structure of the crystal. In the event of a cavity in the granite will be found crystals of quartz and feldspar, perhaps also of mica, as the cavity here means that each has had an opportunity to exercise its tendency to build itself regularly with something of the freedom which a perfect crystal requires. Another familiar example of crystallization is given by the ice covering a pond, which is as truly crystalline in structure as the perfect snow crystal, but here there are no crystals, and it is easy to understand why. The slow dissection of the mass, however, under the melting action of the sun, reveals something of the regularity in the molecular building, and the same thing is proved by an examination in polarized light. Sometimes, in the freezing of a little pool of water, the formation of the slender crystalline ribs of ice may be watched as they shoot out, forming a framework which may soon lose its distinctness as the entire surface is frozen over. Edward S. Dana, in his Minerals and How to Study Them, defines a crystal as the regular solid form which a chemical substance takes when it passes into the solid state from that of either a liquid or a gas, if under such conditions that the molecules are quite free to arrange themselves according to the direction of the attractive forces acting between them. The crystal is, therefore, the outward expression of the structure in the arrangement of those molecules, and its form is for this reason the most important of all the physical character of a given species, and the one which in general most definitely distinguishes it from others. Crystals are therefore, says Professor Dana, the perfect individuals of the mineral kingdom. The mineral quartz has a specific form and structure, as much as a dog or an elm, and is as distinct and unvarying as regards those characters, although owing to controlling causes during formation these forms are not always assumed. In whatever part of the world crystals of quartz may be obtained, they are fundamentally identical. It is interesting to note that a small crystal is just as perfect and complete an individual as a similar one of great size. There is among the crystals of a given species no such connection between size, on the one hand, and age and maturity on the other, that belongs to the individuals of a species in the animal and vegetable kingdoms. Some crystals are so minute as to be almost microscopic. Others may be of enormous size, as the gigantic quartz crystals occasionally found in the Alps, or the equally large beryl crystals from New Hampshire. A cave opened a few years ago at Maycomb, New York, contained 15 tons of great cubic crystals of fluorite. Another cave in Wayne County, Utah, contained a great number of enormous crystals of gypsum, some of them 3 feet or more in length. But the very small crystals and the like ones of enormous size are not essentially different, except in this comparatively unimportant respect of magnitude. It is seldom that any mineral crystallizes alone. Usually 2 or 3, under quite different crystalline laws, form together. They do this, comments Ruskin, absolutely without flaw or fault, when they are in fine temper, and observe what this signifies. It signifies that the 2 or more minerals of different natures agree somehow between themselves how much space each will want, agree which of them shall give way to the other at their junction, or in what measure each will accommodate itself to the other's shape. And then each takes its permitted shape and allotted share of space, yielding or being yielded to, as it builds till each crystal has fitted itself perfectly and gracefully to its differently natured neighbor. This seems to imply both concurrence and compromise, regulating all willfulness of design, and, more curious still, the crystals do not always give way to each other. They show exactly the same varieties of temper that human creatures might. Sometimes they yield the required place with perfect grace and courtesy, forming fantastic but exquisitely finished groups, and sometimes they will not yield at all, but fight furiously for their places, losing all shape and honor, and even their own likeness in the contest. All crystals belong to one of 6 classes or systems, which are named as follows: isometric, tetragonal, hexagonal, orthorhombic, monoclinic, and triclinic. The principal forms of the isometric system are the cube, octahedron, dodecahedron, the 2 trisoctahedrons, the tetrahexahedron, and the hexoctahedron. The cube has 6 equal faces, each one of which is a square, and the angle between any 2 faces is a right angle or 90 degrees. Galena and fluorite often occur in cubes. A regular octahedron has 8 like faces, each a triangle with equal sides and 3 equal angles, each 60 degrees. Magnetite is often in octahedrons. The rhombic dodecahedron has 12 equal faces, each of which is a rhomb with plane angles of 60 degrees and 120 degrees, while the angle between 2 adjacent faces is 120 degrees. This is a common form with garnet. A trapezohedron has 24 equal faces, each a four-sided figure or trapezoid. There may be a large number of different trapezohedrons, all having the same general form, but differing in the angles between the faces. A similar remark may be made about each of the other type forms of this system. A tetrahexahedron is a 24-faced solid, each face an isosceles triangle, and four together having the same position as the face of a cube. A hexoctahedron is a 48-faced solid. Each face is a scalene triangle, and six faces have the same general position as a face of an octahedron. The isometric system is defined as that system in which the faces are referred to three equal axes at right angles to each other. These axes pass through the centers of the crystals. It will be seen to be true of all these, as it is of all their combinations, that the arrangement of the faces is the same about each one of the six cubic faces, or in other words, about the ends of the three axes. There are also several other forms belonging to the isometric system, but which are described as half forms, or forms in which only half of the faces in the corresponding whole form are present. To them the rules of symmetry do not apply, but their faces are also referred to three equal axes at right angles to each other. The most important of these half forms are the tetrahedron and pyritohedron. The tetrahedron is a form with four equal triangular faces, each of them an equilateral triangle. The pyritohedron is a 12-sided solid, or dodecahedron, each face of which is a pentagon, but not here as with the pentagonal dodecahedron of geometry, a regular pentagon. In crystallography, the name dodecahedron is usually given only to the rhombic dodecahedron, and this form, the pyritohedron, takes its name from the species pyrite, or iron pyrites, because of common occurrence with it. The chief forms of the tetragonal system are the two square prisms and pyramids, and the right-sided prism and double eight-sided pyramid. The square prism has, like the cube, angles of 90 degrees between the faces, but it differs from the cube because the four vertical faces are not like the two end faces, or basal planes. This is often shown in a crystal by the difference in the smoothness of the two kinds of faces, or there may be an easy fracture or cleavage parallel to one set of planes and not to the other. The square pyramid looks somewhat like a regular octahedron, but here the faces are isosceles triangles, not equilateral, and the angle between two faces over a horizontal edge differs from that over one of the vertical edges. In fact, either angle is characteristic of a given species and differs from one species to another. The tetragonal system is defined as that in which the planes are referred to three axes at right angles, of which the two in the horizontal plane are equal, and the third or vertical axis is longer or shorter. In this system there are also some half forms, but only one, the sphenoid, is important. The sphenoid is a four-faced solid looking like a tetrahedron, but differing from it since the faces are isosceles, not equilateral triangles. The chief forms of the hexagonal system are the two six-sided prisms, the two double six-sided pyramids, and the 12-sided prism and double 12-sided pyramid. The angles of the hexagonal prism are exactly 120 degrees, and the terminal face or basal plane is a regular hexagon. The faces of the hexagonal pyramid are isosceles triangles, differing in angle according to whether the pyramid is more obtuse or acute. These angles, and the others that depend upon them, are characteristic for a given species. There is also another hexagonal prism and pyramid diagonal to the others and looking much like them. These two sets correspond to the two square prisms and pyramids of the tetragonal system. There is also a prism bounded by 12 similar faces, and a double pyramid bounded above and below by 12 triangular faces. This double 12-sided pyramid is often called a berylloid because common with crystals of beryl. The hexagonal system is defined as that in which the planes are referred to 4 axes, 3 in a horizontal plane, equal and cutting each other at angles of 60 degrees, and the 4th vertical axis either longer or shorter. All hexagonal forms have 3 equal planes of symmetry making angles of 60 degrees with each other, also another set of 3 diagonal to the others, and a 7th plane parallel to the top or base of the crystal. There are several half forms in the hexagonal system, the most important being those of the rhombohedral system. The important forms are the rhombohedron and the scalenohedron. The rhombohedron is a 6-sided solid, each face of which is a rhomb. The scalenohedron is a 12-sided solid, looking a little like a double 6-sided pyramid, but the faces are scalene triangles and the edges zigzag up and down like that of a rhombohedron instead of horizontal as in the pyramid. The number of species crystallizing in the rhombohedral division of the hexagonal system is very large, and some of them, as for example calcite, are very highly complex. The characteristic forms of the orthorhombic system are the rhombic prism and pyramid. There are also other forms called domes. In a rhombic prism, the terminal face, formed by the basal plane, is a rhomb, not a square as in the square prism, which it somewhat resembles. There may be a great many rhombic prisms on the crystals of the same species, differing in the angles of their 2 edges. The rhombic pyramid in cross-section, like the prism, is a rhomb, and its edges belong in 3 sets, with different angles for each. These angles are characteristic for the crystals of a given species. The forms called domes derive their name from the Latin for house, domus, because when they meet above, they make a horizontal edge like a hip roof. These domes are often and very conveniently called horizontal prisms. In the orthorhombic system, the planes are referred to 3 unequal axes at right angles to each other. The grouping of faces about the extremities of each of the axes differs from that about the others, but there are 3 planes of symmetry which are all unlike. In an oblique rhombic prism, the end plane is rhombic in form, but it is oblique to the faces of the prism instead of being at right angles as described in the orthorhombic system. This oblique prism and a variety of other forms of the same group belong to the monoclinic system, in which the planes are referred to 3 unequal axes, 2 of the angles between which are right angles, while the 3rd, in front, is obtuse. Monoclinic forms are very complex, and for technical description it is necessary to consult a larger work which has space to deal with the geometrical names of the prisms. They have only 1 plane of symmetry and appear as prisms, pyramids, and domes. Finally, there is one other group of forms which belong to the triclinic. In this system, the planes are referred to 3 unequal axes, all oblique to each other. Here all the intersections are oblique, and the like faces are in pairs only on opposite sides of a crystal. There is no plane of symmetry at all. Triclinic forms are even more complex than those of the preceding systems. End of section 28. Section 29 of The Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Availle in January 2016. The Science History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology. Chapter 14. Crystallography. Part 2. Most of the crystals of minerals would give a very poor impression of nature's workmanship to one who expected always to see them exactly like carefully made models or like the regular geometrical figures drawn of them. The cubes of galena are often flattened or drawn out. But it is not really to be supposed that the forms are badly made, like a bad model. On the contrary, the size of the like faces on a crystal may vary, and so the shape of the solid as a whole, but the angles between them remain the same. Moreover, what is really essential is not the size or shape of each face, but the way in which the little molecules of which the whole is built up are arranged. For example, in a cube the essential point is the fact that the structure is the same in the direction of the three cubic faces. It follows from this that in the cube not only are the angles between two adjacent faces always 90 degrees, but the 6 cubic faces are all similar, and therefore, if there is the easy fracture, called cleavage, parallel to one cubic face, there will be also the same cleavage parallel to the others. But the actual size of the faces is a matter of no importance. In fact, in one species the cubes are sometimes lengthened so as to be like fine hairs. Similar remarks can be made in regard to any distorted form. The symmetry in the molecular structure, and hence the angles between the faces, remain unchanged, although the symmetry of the external geometrical form is not that of the ideal crystal. A cube may in nature look like a square prism, for the angles between the faces are all right angles in both cases, but the molecular structure of the two is not to be confounded. In the square prism there is the same arrangement in the transverse directions, but a different one up and down. Hence the square top of the crystal is not like the 4 similar oblong vertical faces, and there is cleavage parallel to one set and not to the other. From this variation it is evident that the practical study of natural crystals is much more difficult than the study of the models which gave the ideal forms. This is especially true because most crystals are so implanted on the rock or embedded in it that only part of the form has been developed. Thus, quartz crystals are often attached at one extremity, while only the other end has had a chance to grow freely. Or the crystals may be implanted upon a surface of rock so that only a series of minute faces and angles are visible. In such cases the study of the form is really a difficult matter requiring much skill and experience. Besides the crystals that have been just spoken of, which, while they look at first irregular, are really perfect in the matter of the position of the faces and of the angles between them, there are others which are really deformed. Some peculiar condition attending the growth of the crystal, or perhaps some force which has acted upon it since it was formed, has resulted in bending or twisting it out of its normal shape, so that it may differ widely in angle from the regular form. Thus the faces may be curved as with the barrel-shaped crystals of pyromorphite, or like the peculiar convex faces common on crystals of the diamond, or the whole crystal may be bent, as is seen sometimes in crystals of quartz, stibnite, or of some kinds of chlorite. Aside from this curving and twisting, a crystal may have had its shape more or less changed by some force exerted in the rock since it was made. It may even have been broken and again cemented together, so that many irregularities may result. The salt crystals sometimes show distinctly one face only with the depression in the center, so that they are called hopper-shaped crystals. The cavernous crystals of pyromorphite and vanadinite give other examples. Crystals, often for the same reason, enclose foreign substances, sometimes in the form of liquids, as the quartz crystals that contain water, occasionally with a movable bubble of air. Or the liquid may be carbon dioxide, then often with a bubble of the same substance in the form of gas. In such cases the crystal must have been formed under great pressure, sufficient to keep the gas in the liquid form. Fragments of such crystals heated in the gas flame fly to pieces with great violence, because of the expansion of the gas formed from the liquid by heat. A peculiar class of false forms in which the crystalline shape does not belong to the chemical substance must be briefly described here. These are called pseudomorphs. Pseudomorph means false form, and the name is applied to a specimen having the form characteristic of one species and the chemical composition of another. This seemingly difficult contradiction is easily explained. Most chemical compounds are liable to undergo a change or alteration when subjected to certain conditions, as moisture, the action of alkaline waters, or acid vapors. Now, in these cases, if the original mineral was in crystals, the external form is usually preserved, often perfectly, while the chemical nature and the molecular structure have changed. The cases where the original substance has entirely disappeared and some other has come in to take its place are also called pseudomorphs. Thus, occasionally, quartz is found in the form of calcite, or of fluorite, or of barite, that is, pseudomorph after one of these. Also tinstone in the form of orthoclase feldspar, native copper in the form of aragonite. Even fossil wood may be said to be a pseudomorph of quartz or opal after the original wood, the structure of which it sometimes preserves with wonderful perfection. Some crystals occur isolated and alone, and then the form is usually developed on all sides, and with something of the regularity which the ideal model shows. Thus are found perfect garnets in mica schist or granite, and gypsum crystals in clay. But it is still more common to find crystals grouped together either irregularly, as in the majority of cases, or perhaps in parallel position, or again in the peculiar way called twinning. It is evident that, since the crystals on a single specimen of a species may be grouped in a great variety of ways, it is not always easy to decide whether a given case is a twin or not. This often becomes a matter requiring careful study, exact measurement of angles, and calculation, perhaps also of optical study. For example, it is common to find quartz crystals crossing each other at a great variety of angles, but true quartz twins are rare. The two parts of a true twin are usually symmetrical with reference to the twinning plane, and there is always the reversal of one half. One very common case of the grouping of crystals, which is apt to be confounded with twinning, is where the crystals or parts of crystals are parallel to each other, so that the axes of all have the same directions and are not inclined as in most twins. This is illustrated by a pile of cubes with faces parallel and having re-entrant angles between them. The crystals of many species are at times arranged in this way, but in every case it will be found that if the complex group is held so as to reflect the light from a window, the faces in adjoining crystals, which reflect at the same time, are always similar faces. An octahedron of fluorite, built up of a multitude of little cubes in parallel position, is a not very rare example of this. Parallel grouping is most interesting when the result is to build up a compound form with branching and rebranching parts like the limbs of a shrub or tree, and hence giving rise to a kind of structure called arborescent or dendritic. Here all the crystals or parts of crystals have their axes in the same direction. The common method of grouping of crystals, however, is quite irregular, and it is only exceptionally that twins or parallel groupings are noted. Minerals are not always in distinct crystals, like those of garnet or quartz, or even in aggregates of crystals. On the contrary, many of the specimens in a mineral cabinet show no crystalline faces at all, and then they are simply called massive. There are, however, important distinctions of structure between massive minerals. First of all, the distinction between crystalline and amorphous must be well understood. A piece of clear quartz, or rock crystal as it is often called, is said to be crystalline. A piece of glass, which very likely the eye alone could not distinguish from it, is amorphous or formless. For the mass of quartz, though it has no definite external form, but is bounded only by irregular fracture surfaces, is just as truly crystalline in structure as a perfect crystal. This is true because the essential idea about a crystallized mineral is that there should be the regular arrangement of the molecules out of which it is built up. It is not always easy, often impossible, with the eye alone to decide whether this regularity of structure exists. It is shown by the cleavage, but when there is no cleavage, it is usually by optical examination in what is called polarized light that this can be most easily proved. For example, the bright colors given by a thin fragment of a quartz crystal in polarized light shows at once, to one who understands the subject of optics, that it is crystalline in structure. In the glass, on the other hand, the molecules have no definite arrangement at all, and hence no action on polarized light. The changes of matter which appear in crystallization, distorted and denuded of their grace as they are often found to be, still reveal great laws which never fail, and to which all change is subordinate, and which appear as such to accomplish a gradual advance to lovelier order, and more calmly, yet more deeply animated rest. Nor has this conviction, says John Ruskin in his somewhat fantastic and humanizing, yet graceful Ethics of the Dust, ever fastened itself upon me more distinctly than during my endeavor to trace the laws which govern the lowly framework of the dust. For, through all the phases of its transition and dissolution, there seems to be a continual effort to raise itself to a higher state, and a measured gain through the fierce revulsion and slow renewal of the earth's frame in beauty and order and permanence. The soft white sediments of the sea draw themselves, in process of time, into smooth knots of sphered symmetry. Burdened and strained under increase of pressure, they pass into a nascent marble. Scorched by fervent heat, they brighten and blanch into the snowy rocks of Paris and Carrara. The dark drift of the inland river, or stagnant slime of inland pool and lake, divides or resolves itself as it dries into layers of its several elements, slowly purifying each by the patient withdrawal of it from the anarchy of the mass in which it was mingled. Contracted by increasing drought till it must shatter into fragments, it infuses continually a finer ichor into the opening veins, and finds in its weakness the first rudiments of a perfect strength. Rent at last, rock from rock, nay, atom from atom, and tormented in lambent fire, it knits, through the fusion, the fibers of a perennial endurance, and, during countless subsequent centuries, declining, or rather let me say, rising, to repose, finishes the infallible lustre of its crystalline beauty, under harmonies of law which are wholly beneficent, because wholly inexorable. All crystallization, says the same writer again, goes on under and partly records circumstances of this kind, circumstances of infinite variety, but always involving difficulty, interruption, and change of condition at different times. Observe, first, you have the whole mass of the rock in motion, either contracting itself and so gradually widening the cracks, or being compressed and thereby closing them and crushing their edges, and if one part of its substance be softer at the given temperature than another, probably squeezing that softer substance out into the veins. Then the veins themselves, when the rock leaves them open by its contraction, act with various powers of suction upon its substance, by capillary attraction when they are fine, by that of pure vacuity when they are larger, or by changes in the constitution and condensation of the mixed gases with which they have been originally filled. Those gases themselves may be supplied in all variation of volume and power from below, or slowly by the decomposition of the rocks themselves, and, at changing temperatures, must exert relatively changing forces of decomposition and combination on the walls of the veins they fill, while water, at every degree of heat and pressure, from beds of everlasting ice, alternate with cliffs of native rock, to volumes of red-hot or white-hot steam, congeals and drips and throbs and thrills from crag to crag, and breathes from pulse to pulse of foaming or fiery arteries, whose beating is felt through chains of the great islands of the Indian seas, and makes whole kingdoms of the world quiver in daily earthquake, as if they were light as aspen leaves. And remember, the poor little crystals have to live their lives and mind their own affairs in the midst of all this, as best they may. They are wonderfully like human creatures, forget all that is going on if they don't see it, however dreadful, and never think what is to happen tomorrow. They are spiteful or loving, and indolent or painstaking, with no thought whatever of the lava or the flood which may break over them any day, and evaporate them into air bubbles, or wash them into a solution of salts. And you may look at them, once understanding the surrounding conditions of their fate, with an endless interest. You will see crowds of unfortunate little crystals who have been forced to constitute themselves in a hurry, their dissolving element being fiercely scorched away. You will see them doing their best, bright and numberless, but tiny. Then you will find indulged crystals who have had centuries to form themselves in, and have changed their mind and ways continually, and have been tired and taken heart again, and have been sick and got well again, and thought they would try a different diet, and then thought better of it, and made but a poor use of their advantages after all. And sometimes you may see hypocritical crystals, pseudomorphs taking the shape of others, though they are nothing like in their minds, and vampire crystals eating out the hearts of others, and hermit crab crystals living in the shells of others, and parasite crystals living on the means of others, and courtier crystals glittering in attendance upon others, and all these besides the two great companies of war and peace, who ally themselves, resolutely to attack or resolutely to defend. And for the close you see the broad shadow and deadly force of inevitable fate. Above all this, you see the multitudes of crystals whose time has come, not a set time, as with us, but yet a time, sooner or later, when they all must give up their crystal ghosts, when the strength by which they grew, and the breath given them to breathe, pass away from them, and they fail and are consumed, and vanish away, and another generation is brought to life, framed out of their ashes. End of section 29.
Section 30 of The Science, History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology. Chapter 15, Descriptive Mineralogy, Part 1. There was a time when there was no life upon the earth, and therefore all matter was mineral. This lifeless period extended through untold ages, during which no organic substances were formed, and indeed could not have lived. When, however, the earth's surface became fit for organic introduction, life appeared, and thenceforward the mineral matter in earth, water, and air began to be acted upon by these new agencies, and the living vegetable and animal forms were produced. Life is continually evolving new forms and substance from apparently lifeless matter, endowing it with properties that in the earlier ages it did not possess, yet all life is based upon the mineral. In addition to the formation of living organisms from matter, it should be noted that these living organisms contain large quantities of such matter, such, for example, as carbonate of lime, the mineral which constitutes the limestones, the chalks, and the marbles, making up the shells of the shellfish and the calcareous covering of the coral polyp. And consequently, just as the animals owe a debt to the rocks, so quite a large portion of the rocks in the earth has been formed from the mineral remains of plants and animals, only again to be recombined into organic life. Thus it may be seen that in the same manner as there is a geographical cycle, there is also a mineralogical cycle, as the coral polyp takes the mineral calcium from the seawater, and at death returns it to the mineral kingdom. Man is what he is today, not only because of the cell life of his ancestors, but also because of the mineral characteristics of the substances of which they were originally formed. A mineral has been well defined as a homogeneous substance of definite chemical composition, found ready-made in nature, and not directly a product of the decay or the life of an organism. It is evident from this definition that the term mineral would apply to an enormous variety of substances. However, only those which possess at least a fair economic importance will be treated in the following pages. One of the best known and at the same time one of the most valuable of minerals is the diamond. In regard to this stone, E.S. Dana, in his Minerals and How to Study Them, gives the following description. The diamond is usually found in distinct isolated crystals, most of them very small, but sometimes as large as a robin's egg or even larger. The crystals are commonly octahedrons, though less often some of the other forms of the isometric system are observed. The natural crystals before cutting, rough diamonds they are called, frequently have rounded edges and curved faces, or the faces show little pits. The hardness is higher than that of any other species, and the specific gravity is also high, 3.5. The luster is very brilliant. The brilliancy of the diamond, however, is much greater when cut with many facets than in the natural crystals. The most highly priced stones are colorless, but it sometimes occurs as pale yellow, green, pink, or blue. The diamond consists of pure carbon, and has thus the same composition as a piece of charcoal. Diamonds are used for cutting glass, and in the form of powder in grinding diamonds and other hard gems. The black, coal-like diamonds, set in a collar and rotated rapidly by machinery as a diamond drill, cut quickly through the hardest rocks, leaving a core behind, which is raised at intervals. A well boring is thus easily made. Graphite, or plumbago as it is often called, is usually found in massive forms which may be separated easily into thin leaves or plates, and hence are said to be foliated. Sometimes also it is finely granular and compact. It has the same composition as the diamond, consisting also of nearly pure carbon. It is, however, a different substance in its physical characters and is hence a distinct mineral. Note that they differ in crystalline form. Also, the diamond is hard and heavy, while graphite is soft and light. Graphite is the so-called black lead of the lead pencils, but it is only like lead in its color. It is an excellent lubricator because of its smooth, soapy character when pulverized. Also, mixed with clay, it is used for making crucibles because it is infusible and not affected by the heat of an ordinary furnace. In electroplating because it is a conductor of electricity. Carbon is also the element which forms the essential part of the different kinds of coal and of mineral oil or petroleum. Anthracite, the coal of eastern Pennsylvania, contains 85 to 95% of carbon and has a bright, shiny surface and conchoidal fracture. It burns with a pale, feeble flame without smoke. Bituminous coal is black to dark brown in color, often dull and with a pitchy luster. It contains less carbon than anthracite, usually 75%, and more hydrogen and oxygen. It burns with a yellow, smoky flame. Brown coal or lignite has a brown color, dull luster, often retains the structure of the original wood, and contains still less carbon, sometimes only 50%. These different kinds of coal and others related to them, though of great economic value, are not properly mineral species, since they have no definite chemical composition. The same remark applies to asphaltum, bitumen, mineral wax, or ozocerite, the many kinds of mineral resins including amber, and finally mineral oil or petroleum, all of which consist chiefly of carbon. Sulfur is another of the chemical elements occurring in nature. It is found in crystals of the orthorhombic system. A common form is an acute rhombic pyramid. It also occurs in masses and in powder. It is soft and, though brittle under the blow of a hammer, is easily cut by the knife. The specific gravity is about 2. It has a resinous luster and a bright sulphur yellow color and streak. The crystals are often clear and transparent. It is used for making sulphur matches. It is one of the 3 substances of which gunpowder is made, with charcoal and niter. It is used in preparing the rubber gum for overshoes and other purposes, also in making sulfuric acid, and in many other ways. Although it cannot be preserved in a mineral cabinet, ice, the solid form of water, is as truly a mineral as diamond or quartz. It occurs in crystalline forms of the hexagonal type, often of great complexity and beauty, as seen in snow crystals. The ice grains that make the pellets of hail, not infrequently occurring with summer thunderstorms, are also occasionally in clusters of crystals, somewhat resembling the hexagonal pyramids of quartz, though this is the exception. Generally, there is simply a concentric concretionary structure. The ice of the pools and ponds is always crystalline, though it is usually only in the first stages of the process of freezing that the crystals are separately visible. Arsenic is found occasionally as a mineral and then called native arsenic. It has a metallic luster and tin-white color, but soon tarnishes on the surface to a dull dark gray. It is also brittle. It is used with copper and tin to form the alloy called speculum metal, useful for metallic mirrors because of the brilliant surface it takes when polished. The lead employed for making shot contains a small amount of arsenic. The compounds of arsenic find various uses, as pigments, sulfide, as a preservative, a poison for insects, white arsenic and Paris green, also in dyeing and medicine. Antimony, like bismuth, is usually included among the metals, for it has a high metallic luster, although its structure is crystalline and it is quite brittle. It is a very easily fusible metal and is useful in the arts because of the alloys which it forms with lead and tin, to which it imparts greater hardness and durability. Native antimony is a bright tin-white mineral with metallic luster and commonly showing brilliant cleavage surfaces. Bismuth is silver-white in color with a reddish tinge and has a bright metallic luster. It is rather brittle and shows a crystalline structure with perfect cleavages. It is, however, nearer to the true metals than either arsenic or antimony. Native bismuth is a rare mineral. Some of its alloys have the curious property of contracting instead of expanding with heat. Bismuth is also employed in medicine in the form of the subnitrate. Another compound is used as a cosmetic. Other uses are in calico printing and to give luster to porcelain. Molybdenite is the sulfide of the rare element molybdenum. Like graphite, which it much resembles, it occurs in foliated masses or in crystalline plates having a hexagonal outline, rarely in distinct hexagonal crystals. It is also very soft, with a soapy feel, and leaves a trace on paper. Gold is the most highly prized of the metals, valued because it serves as the money of all civilized people, and because of its use for ornaments. It is sometimes found in isometric crystals, as in octahedrons, but usually in plates or scales or wire-like forms. Also in larger masses, called nuggets. It is soft and can be cut by the knife. It is highly malleable and ductile, and especially remarkable because it can be hammered out into very thin sheets. The skillful gold beater can make the plate so thin as to transmit a faint greenish light. Gold occurs mostly in veins in the older crystalline rocks, especially associated with quartz. Gold quartz is quartz, often milky, which either shows little particles of gold scattered through it, or from which gold can be obtained, even if not visible to the eye, after the rock is crushed to powder and then washed to remove the lighter material. A large part of the gold of the world has been obtained from the sands and gravels produced by the disintegration of gold-bearing rocks. These gravels in the bed of a stream may be washed by the miner in his pan, or on a large scale where a powerful stream of water is thrown against the gravel bank, carrying away the lighter rock and leaving the heavy gold particles behind, usually in the form of little flattened scales. Platinum is reckoned among the nobler metals with gold, and like it is not attacked by any of the single acids. It has a rather dull gray color and is not a beautiful metal, although now more highly valued because of its practical uses than any of the metals except gold. It is rarely found in isometric crystals, as in cubes, more commonly in scales or in larger masses, up to 20 pounds, called nuggets, washed out of the gold sand. The fact that it is fused with great difficulty and is not attacked by ordinary chemical reagents makes it very valuable both to the chemist in the laboratory and in the chemical manufactories, where crucibles and dishes are made of it. It is also largely used by dentists. It has come into use of recent years for the attachments to the ends of the carbon wire in the incandescent electric lamp. Silver is one of the precious metals, useful alike as money, for ornaments of many kinds, and for utensils. The color is a fine silver white when perfectly fresh, but it is easily tarnished, and the presence of sulfur in the atmosphere soon turns it black. Native silver is not an uncommon mineral, although the world's supply of the metal comes chiefly from its ores. It is like gold in its occurrence, sometimes, though rarely, in distinct isometric crystals, more frequently in arborescent or branching groups, in plates and scales or wire-like forms, sometimes in fine threads. It is highly malleable and ductile, and it is the best known conductor for both heat and electricity. Mercury is a remarkable metal because it is a liquid at all ordinary temperatures, only freezing or becoming solid at -40 degrees. It has a silver-white color and brilliant metallic luster, and is so mobile that from early times it has been called quicksilver. Its density is high, 13.6, or higher than silver, 10.6, and lead, 11.4, and for this reason and because of its liquid form it is of great value for scientific purposes. It is used in most thermometers and barometers, and is employed in many experiments in the physical and chemical laboratories. It also has the property of forming a pasty mass or amalgam with some of the other metals, as gold and silver, also copper, zinc, tin, etc., but not iron, and is hence of great value in separating them from the rock in which they occur. Ordinary mirrors are made of glass, backed with an amalgam of mercury and tin. Mercury in various forms is also used in medicine, but in minute doses, for it is an active poison. Corrosive sublimate is a chloride of mercury. Native mercury is a rare mineral in nature, though occasionally found in minute globules scattered through the rock. The common ore is cinnabar, the sulfide of mercury, sometimes called natural vermilion, which is found in masses of a fine red color, and sometimes also in small rhombohedral or prismatic crystals. The luster is adamantine, and the color bright cochineal red, sometimes becoming dull and dark. The streak is scarlet. Crystals are usually perfectly transparent. Copper is one of the most useful of the metals, having been employed for utensils and in other forms, both as a metal and in different alloys since very early times. Of recent years its use has been increased very largely because of its good conductivity for electricity. It thus forms the material of the wires of the dynamo machines, those by which the electrical current is carried for the electric light, the trolley, etc. Copper is also extensively used for electroplating, as in making stereotype plates. It forms further a large number of useful alloys, of which brass, an alloy of copper and zinc in the ratio of about 2:1, is the best known. In the various kinds of bronze, bell metal, gun metal, antique and metal bronze, etc., copper is also the prominent metal, alloyed with tin. In aluminium bronze it is alloyed with aluminium. In German silver it is alloyed with zinc and nickel. Copper is obtained in nature in the native state, and also from a variety of valuable ores, which are some of the most interesting and beautiful minerals. Fool's gold, chalcopyrite or copper pyrites, is the beautiful deep brass-yellow copper mineral, often called yellow copper ore. The color is so golden that it is not infrequently mistaken for gold, especially when scattered in small particles through a mass of quartz. Malachite, the carbonate of copper, is a bright green mineral, often found with native copper, cuprite, and other copper ores because of the readiness with which they are converted into the carbonate by the action of the carbon dioxide present in the air or dissolved in the water. When close and compact, it can be cut and polished, and thus forms a handsome ornamental stone. Azurite, or the blue carbonate of copper, is not so common as malachite, but it is also a beautiful mineral, and when in large transparent crystals of a fine deep blue, it forms one of the most attractive specimens in a cabinet. The crystals are oblique rhombic prisms. Lead is one of the most important of the metals, and even pure is used for many purposes familiar to all, as for pipes to convey water and for shot and rifle balls. It has a dull blue-gray color. It is very soft and malleable. It is often alloyed with other metals, thus with tin in common solder and pewter, with antimony in type metal, with arsenic in small amount for making shot. White lead, the carbonate, is largely used in making paint, also the oxide, red lead. The supply of the metal, which is used so largely, is obtained from its ores, especially the sulfide galena. The latter is one of the commonest of minerals, occurring in large deposits in many mining regions. It is also used for glazing common stoneware, and hence it is called potter's ore. Tin, one of the most important of metals for a great variety of technical purposes, occurs, if at all, only very rarely in nature in the native metallic state. The supply is obtained almost solely from a single ore, the mineral cassiterite or tin stone. The use of tin that first suggests itself is for tin plate, so largely employed for vessels, roofing, etc. This is simply sheet metal coated with metallic tin. Tin enters into many alloys, as the various forms of bronze, gunmetal and bell metal, etc., in which it is alloyed with copper. It also forms alloys with lead in pewter and several kinds of solder, with antimony in Britannia metal, with both lead and antimony in Queen's metal, and copper and antimony in Babbitt metal, with lead and bismuth in fusible metal. Cassiterite or tin stone occurs when crystallized in square prisms and pyramids and other related forms. Twin crystals are common. The crystals have a splendid adamantine luster and a brown color, sometimes nearly black. Iron may well be called the most important of all the metals. How large a place it takes in the work of the world is shown by the fact that each year some 50 million tons are produced from its various ores and turned into some of the many forms needed by man. The entire supply of iron which the world uses each year is obtained from its ores, in which the iron is in combination chiefly with oxygen. These ores are the minerals hematite, magnetite, and limonite. Siderite, the carbonate of iron, is also an important ore. The meteorites which occasionally fall to the earth often consist entirely of metallic iron. Magnetite suggests in its name its most striking character, that of being magnetic. All kinds are strongly attracted by a magnet, and one variety, called the lodestone, found for example at Magnet Cove, Arkansas, is a powerful magnet itself. It has a north and south pole, the power of picking up particles of iron or steel, as tacks, and also, when suspended, it sets with its poles north and south like a compass needle. End of section 30. Section 31 of the Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 2, edited by Francis Rolt-Wheeler, Geology. Chapter 15, Descriptive Mineralogy, Part 2. Nickel, though formerly a little used metal, has become of much wider application in recent years. It is extensively employed now to plate many articles of steel, as knives, scissors, skates, etc., because unlike the steel it does not tarnish or rust rapidly in the air. It is much used also when alloyed with copper for small coins, as the nickels or 5-cent pieces of this country, and similarly in Switzerland, Germany, and Belgium. Nickel steel has been found to be remarkably strong in withstanding the blow of a cannonball. The white alloy called German silver contains copper, zinc, and nickel in about the proportions of 5 to 3 to 2. There are not, however, many minerals which contain nickel. One of these is the sulfide millerite, another is nickelite or nickel arsenide. Cobalt is a metal related to nickel and often associated in nature with it in its various compounds, though of much more limited occurrence. As a metal, it is not used in the arts, but its salts, which are most brightly colored, have some applications. From the change in color that certain of them undergo on heating and on losing water depends their use as sympathetic ink. Cobalt glass, called smalt, has a beautiful blue ultramarine color, and ground up is used as pigment. Manganese is a metal which is closely allied to iron in physical characters and chemical relations. As obtained by the chemist, for it does not occur in nature, it is hard and brittle. Like iron, it forms numerous natural compounds, but they do not find many applications in the arts. Zinc is one of the most common and important of the metallic elements, but it is not certainly known to occur in the form of the metal in nature. It has a crystalline structure like metallic antimony, a white color, and brilliant luster, soon, however, tarnishing. It is brittle at both low and high temperatures, but at 140 degrees centigrade it can be rolled into sheets. It is a most important metal in the arts. Iron in sheets and wire coated by zinc are protected from rusting, and are then said to be galvanized. A common use of the sheets is for roofing. Zinc is the negative metal in almost all forms of the chemical electric battery, that is, the metal at the expense of which the electric current is obtained. With copper it forms brass and related alloys. It is also one of the constituents in German silver. An alloy of zinc is used for making raised cuts in photo engraving. The white oxide is used for paint. Metallic zinc, as obtained from the furnace in ingots, is called spelter. Aluminium is one of the most remarkable of metals, because while it has great tenacity and is in a high degree sonorous and non-oxidizable in the air, it has a specific gravity of less than calcite, or only 2.5. In other words, it is only about 1/3 as dense as iron and 1/4 as dense as silver, which it somewhat resembles. Both as the pure metal, because of its low density, and in alloys, for example, with copper as aluminum bronze, because of their strength and other remarkable properties, it is highly useful. Corundum, oxide of aluminum, is, next to diamond, the hardest of minerals and one of great interest. Its clear blue varieties make the sapphire of jewelry, and the clear red the highly prized ruby, while the coarse and impure kinds, when pulverized, are emery, used for grinding. The luster, like that of most very hard minerals, is brilliant and adamantine, though rather dull in some massive kinds. The color is gray to brown or nearly black in many of the common varieties, called in part adamantine spar, bright blue in the variety called the sapphire, red in the ruby, purple in the oriental amethyst, yellow in the oriental topaz. Turquoise, the beautiful precious stone having the color of robin's egg blue, also bluish-green in less highly prized varieties, is a hydrated phosphate of aluminium, containing also a little copper phosphate, which is probably the source of the color. It occurs only in compact massive forms, filling seams and cavities in a volcanic rock. Calcium, whose oxide, CaO, is the familiar substance called lime, is a white metal somewhat resembling silver or tin. Its compounds are numerous and important, and it is indeed one of the most widely distributed of all the elements. Fluorite or fluorspar, calcium fluoride, is one of the most beautiful of minerals, occurring in cubic crystals and groups of crystals, sometimes very large and of a great variety of colors, from colorless to green, yellow, brown, red, and purple. The crystals are usually transparent and sometimes show on or near the surface a bright bluish color, quite different from that observed when they are looked directly through. The blue light extends within the crystal if it is placed in the direct sunlight. This phenomenon is called fluorescence, and having been first observed with fluorite, was named accordingly from it. Calcite, next to quartz, is the most common of mineral species, remarkable for its variety of form, both among the crystallized and uncrystallized varieties. It crystallizes in rhombohedrons and scalenohedrons of great variety and complexity of form, also in hexagonal prisms. A clear cleavage mass of high-grade calcite, such as that brought from Iceland, is called Iceland spar, and is useful for optical prisms. This is because of its remarkable double refraction, or power of dividing a ray of light passing through it into two separate rays, so that a line seen through it appears double. Besides the crystallized kinds, there are those which have a granular structure, as statuary marble, and which sparkle in the light because of the multitude of cleavage faces. Other kinds are fibrous with a silky luster, like satin spar, also close and compact as an ordinary marble, and then of great variety of color, red, yellow, blue, black, and largely used for ornamental purposes. Some of these kinds of marble still contain shells, which come out distinctly when polished. Gypsum occurs in monoclinic crystals. Twin crystals are also common. Gypsum also occurs in fibrous forms called, like the similar variety of calcite, satin spar. It is easily distinguished from calcite because so much softer. The luster is pearly on the face of perfect cleavage, otherwise subvitreous. It is also silky in some fibrous forms, and in earthy kinds dull. When gypsum is heated and the water of crystallization driven off, gypsum becomes the anhydrous sulfate. This is done on a large scale and called plaster of Paris, which is extensively employed for making plaster casts, for the hard finish for walls, and for other uses. Gypsum is also largely used when ground up for improving soils. The variety alabaster is soft and easily cut into vases and other ornamental objects. Magnesium is the metal which is present in the oxide MgO called magnesia. It is a white metal resembling calcium and closely related to it chemically. In the form of a thin strip or ribbon, it burns readily in the air, yielding a very brilliant white light, which is often used as a source of illumination in photography. Barium is a metal only known in the laboratory, where it can be obtained from some of its compounds. It is a heavy metal, and takes its name from this fact from the Greek word for heavy, barouche. All its salts have also high density. Strontium is the metal which is present in the various salts characterized by the beautiful red color which they give to the flame. The nitrate is thus used in fireworks and red fire. The hydrate is used for preparing and refining beet sugar and in extracting crystallized sugar from molasses. The metals sodium and potassium, though obtained with some difficulty, are interesting to the chemist because they combine so eagerly with oxygen. For this reason, they can be preserved only in some non-oxidizable medium, as oil, and a fragment of potassium placed in water takes fire and burns, uniting with the oxygen and liberating hydrogen. Sodium also decomposes water. Halite or rock salt, sodium chloride, is one of the few important minerals which is readily soluble in water and hence gives a decided taste. This taste is familiar to everyone, for halite is simply the natural form of table salt. It crystallizes in fine, clear, cubic crystals with perfect cubic cleavage. It is also found in granular cleavable masses. It has a vitreous luster and is colorless when perfectly pure, but from white it passes through various shades of red and yellow. Occasional patches of a deep blue are seen in the clear crystals. Borax, the sodium borate which is so familiar to the housekeeper, also occurs in nature, and on so large a scale in certain limited regions as to be extensively mined. It is found in monoclinic crystals, often of large size. They are clear at first, but lose water on exposure and become white and opaque. Borax finds many uses in the arts, as in making glass and soap, in soldering, and in medicine. Silicon is, next to oxygen, the most widely distributed of the chemical elements. In fact, it is estimated to make up about 1/4 of the Earth's crust. The element itself is known only to the chemist, who obtains it with some difficulty from its compounds. One form is that of reddish crystals, resembling those of the diamond and almost as hard. The common compound of silicon in nature is the oxide, SiO2, called usually simply silica. The well-known mineral quartz has this composition. Opal is another kind of silica, amorphous and containing some water. Quartz, the oxide of silicon, is the commonest of minerals, and in some of its varieties one of the most beautiful. It makes up most of the sand of the seashore. It occurs as a rock in the forms of sandstone and quartzite, and is a prominent part of many other important rocks, as granite and gneiss. It is a mineral which can be usually recognized by its form when crystallized, also by its hardness, conchoidal fracture, its glassy luster, and infusibility. The color varies widely. Crystals are usually colorless or nearly so, but also yellow and brown to nearly black. There are also pink, green, and red kinds. The massive forms vary still more, and the color is often in bands or clouds. Quartz appears under a great number of varieties, differing particularly in color and structure, and as many have been long used for ornamental purposes, they have received a number of distinct names. Rock crystal, the clear, colorless variety, when quite free from flaws, is used for spectacle glasses, and the Japanese make crystal spheres of rock crystal. Smoky quartz, having a smoky brown color, sometimes very dark. It is cut into ornaments, and in Scotland it is called cairngormstone. Amethyst, a fine purple kind, also used for ornaments. A yellow variety of quartz crystal is called false topaz. Cat's eye may be mentioned, giving when polished a peculiar effect of opalescence, due to fibers of asbestos, which sometimes resembles the reflection from the eye of a cat. The same name is given to other stones having like effects. The highly prized cat's eye of jewelry is a variety of crystal beryl. Chalcedony is a kind having a waxy luster, either transparent or translucent, and varying in color from white to gray, blue, brown, and other shades. Agate is a variegated chalcedony, commonly with the colors arranged in delicate parallel bands, straight, curved, or zigzag. Onyx is, like much agate, made up of layers of different colors, usually white and black or white and brown, but the banding is straight, and the layers are in even planes. The stones may hence be used for cameos, the head being cut from one layer and the background formed by the other. Jasper is an impure opaque colored quartz, often red, colored by red iron sesquioxide, also brown or ochre yellow and dark green. Sometimes the red and green colors are shown in the same specimen, arranged in bands as in ribbon jasper. And flint, which is nearly opaque and has a dull color, usually gray, smoky brown, and brownish black. It breaks with a deeply conchoidal fracture and a sharp cutting edge, and is hence easily chipped, as by the Indians, into arrowheads or hatchets. Opal is a form of silica containing a few % of water. It does not occur in crystals, but in massive and amorphous forms only. These often show a peculiar effect called opalescence, like that of water containing a few drops of milk, and some varieties show a beautiful play of color. The color varies from white to yellow, red, brown, green, gray, and black. It is sometimes transparent, but more commonly only translucent. The most beautiful variety of opal is much admired because of the delicate play of colors, due to the optical effect of internal reflections. The colors are often seen on a white, also on a red, ground. One kind of precious opal with a bright red flash of light is called the fire opal, and another kind is the harlequin opal. A beautiful opal found in Queensland shows an iridescent blue, sometimes like the effect of a peacock's wing. Infusorial earth is a kind of opal silica consisting of the microscopic shells of the minute vegetable organisms called diatoms, and as found in beds, sometimes of great extent, is properly ranked as a mineral and a variety of opal. Electrosilicon is the trade name of one kind much used for polishing silver. The silicious shells are so fine that they do not scratch the surface. A layer of pure white infusorial earth is often found under a peat bed. It would not be easy to estimate the enormous number of the diatom shells which would be required to make up a cubic inch of it. Beryl is one of those species which are almost always in distinct crystals and usually in forms easy to recognize. It is also interesting because some varieties are used as a gem. The hardness of beryl is 7.5, or a little above that of quartz, and on this account and because of the beautiful color it sometimes has its rank as one of the precious stones. The luster is vitreous or glassy. In this respect also it resembles quartz, and the color is usually some shade of green, bluish green in common beryl, clear mountain green in the variety called aquamarine, and a deep emerald green in the highly prized variety emerald. There are also light or dark yellow kinds, sometimes having a rich golden color and occasionally white, and still more rare, pink kinds. Garnet is another species which, like beryl, is almost always in distinct crystals, and as these crystals are commonly isolated and scattered through the rock, it is not difficult to recognize them. There are, however, massive kinds needing some skill for their identification. These are occasionally used in the same way as emery, though much less hard. The luster is vitreous, and the color, while most commonly red, varies also from the colorless kinds to those which are yellow, brown, black, and green. The micas are characterized before all by their very perfect cleavage, in consequence of which they admit of being split into leaves much thinner than a sheet of paper. In fact, it is difficult to set any limit to the extent to which this process may be carried. These leaves or sheets are usually very elastic and spring back with force when bent. The micas are silicates of alumina with potash, rarely soda or lithia, also magnesia, iron, and some other elements. Chrysolite, or olivine, is a silicate of magnesia and iron having a vitreous luster and bright yellowish-green color. The luster is vitreous, and the color, besides that mentioned, may be yellow to olive green and brown. Chrysolite, golden stone, from the Greek chrysos, gold, and lithos, stone, is an old term in the mineralogy of former times given to a number of yellow minerals used as gems, thus to beryl, topaz, chrysoberyl, and zircon. Tourmaline is one of the most attractive minerals among the silicates. Its varieties show a greater range of color than any other species, not even excepting fluorite, and some of the clear pink and green kinds make beautiful gems. It is also always found in prismatic crystals, bounded often by 3 sides, sometimes by 6, also by 9, and not infrequently rounded so that there are no distinct faces to be distinguished at all. Topaz is another gem silicate, beautiful in its fine crystals and in its brilliancy of luster and color. It occurs in prismatic crystals, terminated by rhombic pyramids, sometimes acute, sometimes obtuse. There are also coarse crystals and massive fibrous forms, but these last are not so common. The perfect basal cleavage of topaz is one of its most characteristic points. Hard as it is easily broken in a direction across the prism, and will yield thin plates with very smooth faces. The luster is vitreous, and the color varies from colorless to white, wine yellow, and blue. Pink topaz is sometimes found. Serpentine is a remarkable mineral because of the variety of massive forms it assumes, although it is not known to occur in crystals of its own. The crystals of serpentine which are found are what are called pseudomorphs, having been derived from some other species by chemical change. The most peculiar variety is the fine fibrous kind called chrysotile, not to be confounded with chrysolite. This usually occurs as thin seams in the mass of mineral. Chrysotile may be separated into fibers, very flexible and as soft as the finest silk. This variety is popularly called asbestos, but there is another kind of asbestos of rather similar appearance, which is a variety of the mineral amphibole. These brief descriptions of the principal minerals may serve in some measure to clarify and determine the reader's knowledge of the metals he handles and the stones and rocks whereon he treads. But even so, there are fields illimitable of investigation. These might be pointed out in almost any of the minerals, but the question has been so excellently well worded by Ruskin with regard to marble that it may serve for all. Quote, "Another singular point in the business to my mind," unquote, he says, quote, "is that these stones, which men have been cutting into slabs for thousands of years to ornament their principal buildings with, and which under the general name of marble have been the delight of the eyes, and the wealth of architecture among all civilized nations, are precisely those on which the signs and brands of these earth agonies have been chiefly struck, and there is not a purple vein nor flaming zone in them which is not the record of their ancient torture. What a boundless capacity for sleep and for serene stupidity there is in the human mind. Fancy reflective beings who cut and polish stones for 3,000 years for the sake of the pretty stains upon them, and educate themselves to an art at last, such as it is, of imitating these veins by dexterous painting, and never a curious soul of them all that while asks, what painted the rocks?" Unquote. End of chapter 15. End of section 31.
Section 32 of the Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 2, edited by Francis Rolt-Wheeler, Geology. Chapter 16, Mining and Metallurgy. Among the many minerals which constitute the crust of the earth, there are some which are of such character and occur in such quantities that they possess commercial value, and it is profitable to separate them from their neighbors and apply them to the service of mankind. The process employed in the extraction of these useful minerals are classified under the term mining. The origin of mining retreats into such antiquity as to be most obscure. It is certain, however, that the Phoenicians and Egyptians at the earliest periods of history had an abundance of metals. The Egyptians had mines of copper, silver, and gold in productive operation both on the Ethiopian and Arabian border. The Sinaitic Desert contains the ruins of mining works, probably operated by the Egyptians. Abraham found gold and silver in use among them. In the time of Alexander, gold, silver, copper, and iron were obtained in Ethiopia. In Asia Minor, the gold mines formerly owned by Croesus were worked down to the time of Xenophon, but Strabo says that in his days they were exhausted. The Athenians worked rich silver mines in Attica and gold mines in Thrace. Before the time of the Romans, mining was carried out in many parts of Western Europe. After the conquest of Caesar, the tin of Cornwall was shipped first to the Isle of Wight and thence to the coast of Gaul, where it was loaded upon horses and transported to Marseilles. The early Romans did not work the mines of their native land, but by their numerous conquests gained control of all the important mines of the ancient world. Traces of ancient mining in the United States are found to the copper region of Lake Superior and to certain districts in New Mexico. In both cases, the implements used seem to have been rude hammers of stone. It is evident that in ancient times muscular force, assisted only by applications of fire and occasionally by the power of water, was the miner's resource. A most suggestive picture of rude mining operations is given in the book of Job 28, 1-11, of which Conant's translation brings out the points very strikingly. For there is a vein for the silver and a place for the gold which they refine. Iron is taken out of the dust, and stone is fused into copper. He puts an end to the darkness, and he searches out to the very end, stones of thick darkness and of death shade. He drives a shaft forgotten of the foot, they swing suspended far from men. The earth, out of it goes bread, and under it destroyed is with fire. A place of sapphires are its stones, and it has clods of gold. Against the flinty rock he puts forth his hand. He overturns mountains from the base. In the rocks he cleaves out rivers, and his eye sees every precious thing. He binds up streams that they drip not, and the hidden he brings out to the light. Pliny gives a similar description of shaft-sinking operations. Quote, elsewhere, pathless rocks are cut away and are hollowed out to furnish a rest for beams. He who cuts is suspended with ropes. They go where there is no place for the footprints of man. The removal of surface material by sluicing was also practiced in ancient times in Spain. The Aztecs had an extensive metallurgical industry. They understood how to sink shafts and run tunnels, says John S. Hittel, how to wash gold from alluvial deposits, how to use the bellows and furnace in smelting the ores of copper, tin, lead, and silver, and how to cast metals. They had a little tin and considerable quantities of lead. The Quecans were not less skillful, and they quarried stone with veins of silver on a large scale. They alloyed gold, silver, and tin with copper, so that these metals must have been mined, and a complete knowledge of fluxes in the fusion of ores was known to them. Barbarism generally, which is often regarded as being coupled with the Bronze Age, was obviously possessed of mining, and not only of mining, but of smelting also. Before proceeding with any further discussion of the useful minerals, it is well to understand what is meant by the expression ore deposits. This is clearly set forth by Heinrich Ries in his Economic Geology. Quote, the term ore deposits, he says, is applied to concentrations of economically valuable metalliferous minerals found in the Earth's crust, while under the term ore are included those portions of the ore body of which the metallic minerals form a sufficiently large proportion to make their extraction profitable. A metalliferous mineral or rock might therefore not be an ore at the present day, but become so at a later date because improved methods of treatment or other conditions rendered the extraction of its metallic contents profitable. A few metallic minerals serving as ores, such as gold, copper, platinum, or mercury, sometimes occur in a native condition, but in most cases the metal is combined with other elements, forming sulfides, hydrous oxides, carbonates, sulfates, silicates, chlorides, phosphates, or rarer compounds, the first 5 of these being the most numerous. A deposit may contain the ores of one or several metals, and there may also be several compounds of the same metal present. The terms rich and poor, as applied to ores, are used with great frequency, although most indefinite and often meaningless. Under very favorable conditions, it is possible to profitably work an ore of given value at one locality, while if found under other less favorable conditions at another point, it might be almost worthless. The important ore deposits are not numerous. There are many other ores mined for the metal they contain, but they are either of small economic importance or occur in small quantities in nature. Iron is an abundant constituent of the Earth's crust, and yet few minerals are capable of serving as ores of this metal, and 5 ores supply the greatest amount of the world's iron: magnetite, hematite, limonite, siderite, and pyrite. Magnetite occurs in the United States, 1, as lenticular masses commonly in metamorphic rocks, 2, as more or less lens-shaped bodies in igneous rocks, 3, as sand on the shores of lakes and seas, and 4, as contact deposits, that is, those which form along the surface of contact of igneous and sedimentary rocks. The first class includes the most important deposits now worked in this country. The second and third groups run too high in titanium to have commercial value at the present time, and undoubted representatives of the fourth class of commercial value are not worked. There are some, it is true, which occur along the contact of an intrusive and sedimentary rock, but their origin is ascribed to meteoric circulations. Of all the iron ores, hematite is by far the most valuable, chiefly on account of its easier reduction, but also because of the greater richness of the known important deposits. Most of the deposits mined belong to the replacement type, that is, they are the result of the replacement of a fissure-filling material. Limonite may occur under a variety of conditions and associated with different kinds of rocks, but 2 important types are recognized, namely bog ores and residential limonites. The bog ores are formed by the precipitation of limonite in swamps, ponds, or lakes. Such ores are usually impure from an admixture of sand or clay which has been deposited at the same time, and are rarely of any thickness. They are of no commercial value in the United States, but are mined more extensively in Sweden and Canada. The residual limonites are a much more important class and are formed by the weathering of pyritiferous veins, or more often from the weathering of ferruginous rocks. Siderite is the least important of all ores of iron mined in the United States, both on account of the small quantity and its low iron contents. When of concretionary structure, with clayey impurities, it is termed clay iron stone. Pyrite, though widely distributed in nature, is not used as an iron because of the large amount of sulfur contained. Copper-bearing minerals are not only numerous, but widely, although irregularly, distributed. More than this, copper is found associated with nearly every variety of ore or ore deposit. Nevertheless, but few minerals serve as ores of copper. All the largest copper deposits in the world may be divided into 2 groups. 1. Deposits formed by ascending, circulating, probably hot waters, the ores being deposited in fissures, pores, spaces of brecciation, or sometimes replacement of the rock. And 2. Pod or lens-shaped deposits in crystalline schists, which may represent concentration of material from a disseminated condition in the surrounding rocks. The ores of lead and zinc occur very often associated with each other. Of these, galena is the commonest lead ore, while others are usually found where superficial oxidation of the deposit has taken place. Of the zinc ores, sphalerite, also known as blend, jack, or blackjack, is by far the most important. With few exceptions, zinc is constantly associated with lead, and at times, as in portions of the Cordilleran region, carries silver or even gold. Gold and silver are obtained from a variety of ores, in some of which the gold predominates, in others silver, while in still a third class, these 2 metals may be mixed with the baser metals, lead, copper, and zinc. Few gold ores are absolutely free from silver, so that a separate treatment of the 2 is more or less difficult. Gold occurs in nature chiefly as a native gold mechanically mixed with pyrite, or as a telluride, such as calaverite. Most of the gold and silver mined in the United States is obtained from fissure veins, or closely related deposits of irregular shape in which the gold and silver ores have been deposited from solution, either in fissures or other cavities or by replacement. Considerable gold and a little silver is obtained from gravel deposits. Some true contact deposits are known. Gold has been found to occur in rare instances as an original constituent of igneous rocks and also metamorphic ones, but there are no known deposits of commercial value belonging to this type. The gold and silver ores are sometimes grouped as one, placers or gravel deposits. These serve chiefly as a source of native gold, but may and often do contain a little silver, much of which is never separated from the ore in which it occurs. 2. Quartzose or dry ores, in which the gold and some silver are found in quartz gangue and are either freed or mixed with sulfides, commonly pyrite. 3. Gold and silver bearing copper ores. These are widely distributed throughout the United States and exhibit great differences in form and age. Neither do all of the occurrences yield much gold or silver. And 4. Gold and silver bearing lead ores. This class includes a variety of deposits containing much lead and also silver, with gold usually in subordinate amounts. Since gold and silver ores so vary in their mineralogical associations and richness, the metallurgical processes involved in their extraction are varied and often complex. Those ores whose precious metal contents can be readily extracted after crushing by amalgamation with quicksilver are termed free milling ores. This includes the ores which carry native gold or silver and often represent the oxidized portions of ore bodies. Others containing the gold as telluride or containing sulfides of the metals are known as refractory ores and require more complex treatment. These, after mining, are sent directly to the smelter if sufficiently rich, but if not, they are often crushed and mechanically concentrated. The smelting process is also used for mixed ores, the latter being often smelted primarily for the lead or copper contents, from which the gold or silver is then separated. Low-grade ores may first be roasted and the gold then extracted by leaching with cyanide or chlorine solutions. The introduction of the cyanide and chlorination process, which are applied chiefly to gold ores, has permitted the working of many deposits formerly looked upon as worthless, and in some regions even the mine dumps are now being worked over for their gold contents. The silver-lead ores form a large class which are widely distributed in the Cordilleran region and not only supply most of the lead mined in the United States, but in addition may also, and often do, carry variable quantities of silver, gold, and copper. The deposits as a whole present a variety of forms. The associated rocks are often faulted, and the ore bodies are commonly oxidized above, so that the altered portions require the different metallurgical treatment from the sulfide ores found below. Secondary enrichment has in some cases raised the grade of the ore. Aluminium is one of the few metals whose ores do not present a metallic appearance. Many different minerals contain aluminium, but it can be profitably extracted from only a few. Common clay, for example, presents an inexhaustible supply, but the chemical combination of the aluminium in it is such that its extraction, up to the present time, has not been found practicable. While many different minerals contain manganese, practically the only ones of commercial value are the oxides and carbonates, and in this country only the former. The silicates are not used as a source of manganese owing to their high silica percentage. The several ores of manganese are often intimately associated, the pyrolusite generally assuming a crystalline and the silomelane a massive character. Manganese oxides are also often intermixed with more or less oxide of iron, and considerable amounts of the metal are obtained from magniferous zinc, silver, or iron ores. Since such manganese is used in iron reduction, the last association is of importance. Mercury ores are not confined to any particular formation, but are found in rocks ranging from the Ordovician to recent age in different parts of the world. Nor are they peculiar to any special type of rock. Although igneous rocks are often found in the vicinity of them, they occur as veins, disseminations, or as masses of irregular form. The most important ore of antimony is stibnite, and the metal is rarely obtained from any other mineral, although native antimony has been sparingly found. The stibnite, together with a gangue of quartz and sometimes calcite, usually forms veins cutting igneous, sedimentary, or metamorphic rocks. Antimony has been found at a number of localities in the Cordilleran region, but the great distance of deposits from the railroad, together with the fact that the smelting plants are located in the east, make them of little commercial value, and no domestic production has been reported since 1901. Moreover, the large output of antimony ores and metal abroad, combined with low ocean freights and the absence of any import tax on crude antimony, are of themselves discouraging to domestic competition. Nickel and cobalt can best be treated together, for nearly all the ores containing one are apt to carry some of the other. And furthermore, in smelting, the two metals go into the same mat and are separated later in the refining process. The nickeliferous pyrrhotite is the most widely distributed of the nickel ores and may carry small amounts of cobalt. It is also called magnetic pyrites. The percentage of nickel ranges from a trace to 6%, but an increase above this brings it into pentlandite. The ores of platinum are native platinum and sperrylite. The former is commonly found in placer deposits, but has also been noted in basic igneous rocks rich in olivine, such as peridotite, or in serpentine derived from it. The sperrylite never occurs in large quantities, but has been found in association with nickel and copper ores. Iridosmine and osmiridium are also known to carry platinum. The nuggets found in placers are often regarded as being pure native platinum. This is only partly true. The chief ore of tin is cassiterite with 78.6% metallic tin, but owing to the presence of impurities, the ore rarely shows this composition. Its hardness, imperfect cleavage, non-magnetic character, high specific gravity, and brittleness help to distinguish it from other minerals that are liable to occur with it. Stream tin is the name applied to cassiterite found in placers. Metallurgy is defined as the art of extracting metals from their ores and adapting them to the various processes of manufacture. That this art was practiced in very early times is indicated by references to the use of metals in the oldest written records of the world's history. Among the many stages in the development of primeval man, none can have been of greater moment in the struggle for existence than the discovery of the metals and the means of working them. The names generally given to the three prehistoric periods of man's life on Earth, the Stone, the Bronze, and the Iron Age, imply the vast importance of the progressive steps from the flint knife to the bronze celt, and lastly to the keen-edged steel weapon or tool. The metals chiefly used have been gold, silver, copper, and tin, the last two forming the alloy called bronze, iron, and lead. Of all metallurgical processes, that of separating of lead from its ores is the oldest. Lead smelting was known to the ancient Hebrews, and silver ornaments were found on the site of ancient Troy that were so pure as to show that the Trojans know how to separate silver from lead. Lead ores were wrought by the ancient Egyptians perhaps 3,000 years BC. The value of iron in ancient times is well brought out by the fact that in Homer's Iliad, a mass of iron is mentioned as being one of the prizes at the funeral games of Patroclus. Metallurgical processes of the present day may be divided into mechanical and chemical. Under mechanical are included the various processes of ore dressing or concentration, the object of which is to separate nearly pure mineral from what is of little or no value. The methods of extracting metals directly from the crude ore or from the mechanically separated concentrates fall under three classes. 1. Extraction of the metal from oxides and carbonates by the reducing action of carbon and the treatment of sulfides by the oxidation of the sulfur contained. 2. The extraction of a metal by getting it in solution and replacing it by another. And 3. Amalgamation, or bringing the metal in contact with quicksilver, in which it forms an amalgam. Most metals are obtained ultimately by the use of heat, either by treating the crude ore or the concentrates obtained by some method of ore dressing. It is well, however, before beginning a discussion of the metallurgy of iron and steel, to define just what is the iron and steel of commerce and industry. In Henrie Marion Howe's Iron, Steel, and Other Alloys, they are described as composites of granitic substances, intimate mechanical mixtures or conglomerates of microscopic particles of certain quite distinct, well-defined, simple substances in widely varying proportions. The chief of these substances are ferrite, the microscopic particles of nearly and perhaps perfectly pure metallic iron. It is magnetic, very soft and ductile, but relatively weak, with a tensile strength of about 45,000 pounds per square inch. It is of the isometric system. It always forms a very important part of slowly cooled iron and steel in general. Cementite, A definite carbide of iron, Fe3C, containing 6.67% of carbon, very brittle, harder than hardened steel, scratching glass and feldspar but not quartz, and magnetic. The carbon in slowly cooled steel is chiefly or wholly present as cementite. Graphite, a characteristic component of gray cast iron, of which it usually forms from 2 to 3.5%. It is pure or nearly pure carbon. When it forms during the solidification of the metal, as is usually the case, it occurs in very thin laminated plates or flakes, often 1/8 inch or more in diameter. When it forms within the solid metal at temperatures materially below the freezing point, it occurs, at least under certain conditions, in very fine powder and is then called temper graphite, the temper carbon of Ladybur. Slag, the characteristic component of wrought iron, which usually contains from 0.2 to 2% of it. It is essentially a ferrous silicate, and it is present in wrought iron simply because this variety of iron is made by welding together pasty granules of iron in a bath of such slag, without subsequently melting the resultant mass or in any other way giving the envelopes of slag thus imprisoned a chance to escape completely. The great classes of iron and steel of chief value to the engineer, and probably to the world at large, are essentially intimate mixtures, or conglomerates of the first two strikingly different microscopic constituents, ferrite extremely soft and ductile, cementite extremely hard and brittle, the former like copper, the latter like glass. The properties of several of the classes may indeed be influenced, and very profoundly, by thermal and mechanical treatment, and by the presence in certain of them of slag or of graphite. But the fact of which our attention should be concentrated at first is this, that the difference in properties between the different industrial classes of iron and steel are due chiefly to differences in the ratio which the ferrite bears to the cementite. What has just been said does not apply, it is true, to what is called hardened steel, but it does apply to the great industrial classes of wrought iron and of steel, such as ship, rivet, fencing wire, tube, rail, and tin plate steel, and indeed all structural steels, whether for plates, beams, eye-bars, angle irons, or any like object. The steels which are especially soft and ductile, example the rivet and boilerplate steels, consist chiefly of the soft, ductile, copper-like ferrite, as do those with very high electric conductivity, such as telegraph and telephone wires. In these steels, the proportion of cementite may not exceed 1% of the whole, the rest consisting almost wholly of ferrite. The harder steels, like rail steels, which are called upon to resist abrasion, example the grinding action of the car wheels intensified by the presence of sand between wheel and rail, have a much larger proportion of cementite. About 93% of their total mass is made up of ferrite, and the remaining 7% consists of cementite. This quantity of cementite suffices to increase greatly the resistance to abrasion, while the loss of ductility, which it causes, though very marked, is not dangerously great. Naturally, as the proportion of cementite in steel increases and that of ferrite decreases, the ductility diminishes continuously and the hardness increases continuously. The tensile strength, however, reaches a maximum when the cementite amounts to about 15% of the whole and the ferrite is about 85%. With further increase of cementite, the tensile strength again decreases. The constitution of steel is not in general reported in the percentages of ferrite and cementite, nor indeed are most engineers and metallurgists of today sufficiently familiar with the aspect of the subject to speak of it with confidence. But this is the aspect with which the practitioners of the near future must face, and it is also that which makes possible an understanding of the relation between the composition and properties of these different classes of iron and steel. Instead of saying that a certain kind of steel, for instance rail steel, contains so much cementite and so much ferrite, it is customary to report simply the carbon which that cementite represents. Graphite is an important constituent of cast iron, especially of gray cast iron, but may be regarded as either absent from steel or, if present, only in unimportant quantities. Gray cast iron, the only kind of cast iron which can be widely used by engineers, may be regarded as a conglomerate of the second degree, for it consists first of a mechanical mixture of ferrite with cementite, quite as steel does, while through this mixture as a matrix there is scattered much free carbon in the form of sheets of graphite. White cast iron typically would consist of cementite and ferrite quite as structural steel does, but with a much larger proportion of cementite rising even to 67%, say 4.5% of carbon. Hence the extreme hardness and brittleness of this class of cast iron, so extreme as to exclude it from most engineering uses. Wrought iron consists essentially of a metallic matrix identical with low carbon steel, in which is mechanically mixed a small quantity of slag, a silicate of iron. This slag is not unimportant, yet it is far less important than the ferrite and cementite of the matrix. Steel, hardened by sudden cooling from a red heat, consists essentially of austenite, a solid solution of carbon in iron of varying degrees of concentration. When austenite contains as much as 1% of carbon, it is intensely hard and brittle, and indeed its hardness and brittleness are roughly proportional to the quantity of carbon which it contains. Hence, steel for purposes which require extreme hardness, such as files and other tools for cutting metals and even wood, have from about 3/4 to 2% of carbon, enough to give the degree of hardness required for the special purpose, but not enough to cause a prohibitory degree of brittleness, and they are hardened by sudden cooling. Besides the cutting tools, armor plate and projectiles are made of hardened steel, and therefore consist essentially of austenite. Alloy steels have come into extensive use for important special purposes, and a very great increase of their use is to be expected. The chief ones are nickel steel, manganese steel, chrome steel, molybdenum steel, and tungsten steel. The general order of merit of a given variety or specimen of iron or steel may be measured by the degree to which it combines strength and hardness with ductility. Nickel steel, which endures well the effect of sudden shock, is used widely for marine shafting. It has been used tentatively for railroads, but while it has the stiffness and resistance to wear which they require, too many rails have broken in use. As actually made, manganese steel contains about 12% of manganese and 1.5% of carbon. Its ductility, to which it owes much of its value, is profoundly affected by the rate of cooling. Sudden cooling makes the metal extremely ductile, and slow cooling makes it brittle. Its behavior in this respect is thus the opposite of that of carbon steel. Its great hardness, however, is not materially affected by the rate of cooling. It is used extensively for objects which require hardness and ductility, such as rock-crushing machinery, railway crossings, minecar wheels, and safes. Chrome steel, which usually contains about 2% of chromium and 0.8 to 2% of carbon, owes its value to combining, when in the hardened or suddenly cooled state, intense hardness with a high elastic limit, so that it is neither deformed permanently nor cracked by extremely violent shocks. For this reason, it is the material generally, if not always, used for armor-piercing projectiles. Tungsten steel, which usually contains from 5 to 10 and sometimes even 24% of tungsten and from 0.4 to 2% of carbon, is used for magnets because of its great retentivity, and for lathe and similar metal cutting tools, which are to cut off a very thick slice at each stroke. The great friction, due to the thickness of the cut, heats the tool to a temperature at which the temper of common or carbon steel is drawn. The merit of tungsten steel is that, like manganese steel, it retains its extreme hardness even after it has been heated to 400 degrees centigrade, or 752 degrees Fahrenheit. Under these conditions, the Taylor and White variety retains its cutting power even when the friction is so great that the chips of metal cut are so hot as to glow visibly, and even the edge of the tool itself grows red hot. Molybdenum steel is now often used instead of tungsten, 1% of the former element replacing 2% of the latter, so that the ratio between their effects appears to be that which their atomic weights would indicate as probable. In other words, 1 molecule of molybdenum appears to have the same effect as 1 molecule of tungsten. Today, practically all of the iron ore mined is smelted in the iron blast furnace, and there converted into cast or pig iron. And this is the case whether the resultant iron is to be used in the form of cast iron, or whether it is to be converted into one of the two other great commercial classes of iron, wrought iron and steel. It is true that there are many direct processes by which wrought iron or steel may be made directly from the ore without first converting it into cast iron. for example, without first putting it into more carbon and silicon than it needs in its finished form, and then taking them out at great expense. But the processes of today are a little more than historical of scientific interest. Whatever promise that they may have made in recent decades has been killed by the great cheapening of the blast furnace process. The blast furnace is an enormous shaft, in many cases as much as 100 feet high and 25 feet maximum inside diameter. The furnace is at all times full from top to bottom of a column consisting of coke or other fuel, limestone, and iron ore, though the lower part of this column consists of fuel only. The ore, flux, and fuel are charged through a hopper at the top of the furnace and form a continuous column extending from the top to the bottom. Through openings called tuyeres at the bottom of the furnace, a powerful blast of air, usually highly preheated, is introduced. This burns the fuel, thereby generating an intensely high temperature sufficient to melt the ore, the iron of which has, by the time it has descended to this region, become reduced to the metallic state. Thus the whole column of solid materials descends slowly as its lower end is eaten away, the fuel which it contains being burned away by the blast and the rest of the material being melted away by the heat from the combustion of this fuel. In addition to the descending column of solid material, there is an ascending column of hot gases. The oxygen of the blast introduced at the tuyeres is quickly converted into carbonic oxide by its reaction with the carbon of the fuel which it there meets. Very soon after entering the furnace through the tuyeres, the atmospheric oxygen has been converted into carbonic oxide, which, together with the atmospheric nitrogen of the blast, sweeps up through the furnace in enormous columns at great velocity. There is thus two columns moving in opposite directions, a solid column of ore, flux, and fuel descending very slowly, and a swiftly rising column of hot gases. Any given lump of the solid material passes through the furnace in about 12 to 15 hours, while any given particle of oxygen or nitrogen entering at the tuyeres passes through and quickly escapes at the top, its passage occupying probably only a small fraction of a minute. The iron ore always contains, besides iron oxide, a considerable quantity of siliceous or earthy material called gangue, and the fuel also contains a certain amount of ash. These materials, the gangue and the ash, together with the lime of the limestone, unite to form a single molten mass, the slag, which floats on the top of the molten iron. Two deep holes are provided at the lower end of the furnace, one called the tap hole, at its very bottom for drawing off the molten iron at intervals, and the other called the cinder notch, a very little above this for drawing off the molten slag. These holes are closed with plugs of clay, except at a time when the molten materials are drawn through them. While these two columns, the descending solids and the ascending gases, pass each other, and the hot gas is sweeping up swiftly, the initially cold solid materials descending slowly, the heat of the gaseous column is recovered by being transferred to the descending solids, so that although the temperature of the gases in the neighborhood of the tuyeres is about 2,912 degrees Fahrenheit, the temperature of those which escape from the top of the furnace is only about 572 to 752 Fahrenheit. Owing to the fact that the fuel is burned in immediate contact with the solid materials which it is to heat, and that the products of the combustion are thoroughly cooled in their long upward travel in which they are exposed to cooler and cooler masses of descending solid materials, the thermal efficiency of the blast furnace is very high. The purifying reactions are brought about by 1. In the puddling process by stirring iron oxide in the form of a silicate very rich in that oxide into the molten cast iron as it lies in the thin boiling layer on the hearth of the reverberatory furnace. 2. In the Bessemer process by blowing cold atmospheric air through the molten cast iron in a deep clay-lined or dolomite-lined retort called a converter, the rapidity of the oxidation itself raising the temperature rapidly. And 3. In the open hearth process by exposing the molten cast iron in a thin and very broad layer on the bottom of the reverberatory furnace to an overlying layer of slag containing iron oxide, and usually enriched in that oxide by throwing into lumps of iron ore. In the last process, in addition to this purification of the cast iron by these oxidizing reactions, its impurities are in most cases also greatly diluted by adding much relatively pure steel scrap. If steel is cooled suddenly, it is thereby made harder and less ductile, or even extremely brittle, and it is said to be hardened. The degree to which it is thus hardened increases with the carbon content, so that whereas very low carbon steel is affected only very slightly, steel with 1% of carbon is made as hard and nearly as brittle as glass. The hardness and brittleness induced increase with the rapidity of cooling without limit, but they are apparently nearly independent of the temperature from which the sudden cooling begins. The tensile strength at first increases with the intensity of hardening, but reaches a maximum and then declines. In case of high carbon steel, a moderate rapidity of cooling may give the highest tensile strength, but in the case of low carbon steel, the tensile strength seems to increase with rapidity of cooling without limit. Hardened steel is tempered, that is, the hardening is mitigated or let down by slight reheating, say to 200 or 300 degrees, and the steel is annealed, that is, the hardening is completely removed by reheating farther, say to 600 degrees. After this reheating to 200 or 300 degrees, it is immaterial whether the steel is then cooled suddenly or slowly. The degree of tempering is the same in either case, and the same is substantially true of the higher heating to 600 degrees or annealing. All the best cutlery and tool steel is made by the crucible process, and indeed all for which any considerable excellence is claimed is supposed to be, though often incorrectly. But the great mass of the steel of commerce is made by the Bessemer and the open hearth process, the latter being generally considered the best, and rising from 9 to 53% in the United States, it reveals in a wonderfully true proportion the advance of progress. End of section 32. End of The Science History of the Universe, Volume 2, by Francis Rolt-Wheeler.